A galaxy exists that breaks every rule we know. Nestled within the distant Perseus cluster, NGC 1277 is not just another island of stars. It is a relic, a cosmic time capsule frozen when the universe was young. This ancient galaxy defies everything we understand about how galaxies live and evolve. And hidden within its ancient light are 50 bizarre objects, each one a mystery waiting to unravel. By the end of this journey, you will uncover secrets that challenge the very foundation of modern astronomy. How can a galaxy survive without dark matter? And what monstrous heart beats at its core? What forgotten story does this celestial fossil hold? Are you ready to explore a place where the universe's old rules no longer apply? The heart of NGC 1277 is not a gentle rhythm, but a thunderous, silent beat. At its very center lies a gravitational monster so vast it defies belief. This is the galaxy's monolithic core, a supermassive black hole with a mass of 17 billion suns. To grasp that scale, consider our own Milky Way. Our galactic center holds a black hole named Sagittarius A star, which is massive at 4 million solar masses. Yet the behemoth in NGC 1277 is over 4,000 times heavier. It is not just a large black hole, it is an architectural impossibility. This single object contains nearly 60% of the mass of the galaxy's entire central bulge, the dense collection of stars at its heart. Imagine if a single organ, like your heart, weighed more than half of your entire torso. That is the level of imbalance we are seeing. Every model of galaxy formation says this cannot happen. Black holes and their host galaxies are supposed to grow together in a kind of cosmic symbiosis. Their sizes are linked, but here the black hole is grotesquely, overwhelmingly large for its galactic home. So how did it get there? One terrifying possibility is that it was born this way in the violent dawn of the universe. In that primordial chaos, a direct collapse of an immense gas cloud could have forged a titanic seed, skipping all the usual steps of growth. Another, equally haunting idea is that we are looking at a failed quasar. A quasar is the brilliant, active phase of a feeding supermassive black hole, shining brighter than all the stars in its galaxy combined. Perhaps this black hole feasted voraciously in the ancient past, bloating itself to this impossible size before its fuel ran out, leaving behind a silent, obese relic in a starved galaxy. This core is not just an anomaly, it is a direct challenge, a single object that forces us to question how the universe builds its largest structures. This gravitational monster, however, is not the only rule this galaxy breaks. If we step back from its core and examine the entire structure of NGC 1277, we encounter a second, even more profound strangeness. This galaxy appears to be missing its soul. According to every major theory of cosmology, galaxies are not held together by the stars and gas we can see. They are sculpted and bound by an invisible, mysterious substance called dark matter. Think of it as a cosmic skeleton, an unseen framework of gravity that keeps a galaxy from flying apart as it spins. Without this dark matter halo, a galaxy like ours would simply unravel. Yet when astronomers measured the speeds of stars orbiting within NGC 1277, they received a shock. The stars were moving exactly as fast as they should, if only the gravity from the visible stars and that colossal black hole was pulling on them. The math showed no need for any extra, invisible mass. The dark matter halo, a universal feature of every other galaxy we have ever studied, is simply not there. This is like finding a skyscraper that stands tall and rigid without any steel beams inside its walls. It defies the fundamental engineering of the universe. So what happened to its dark matter? One compelling theory points to the galaxy's dangerous neighborhood. NGC 1277 lives in the dense, violent Perseus cluster, a crowded metropolis of galaxies constantly brushing past and even colliding with one another. It is possible that billions of years ago, as this galaxy plunged through the cluster's hot core, the gravitational tides acted like a cosmic thief, violently stripping away its dark matter halo, leaving behind only the bare bones of visible stars. But there is another, more radical possibility. What if this galaxy never had dark matter to begin with? This idea strikes at the heart of modern cosmology. Our entire understanding of how galaxies form is built upon the foundation of dark matter collapsing first to create gravitational wells, which then attract the normal matter that becomes stars. If NGC 1277 formed without it, we must rewrite that story. Perhaps in the early universe, under unique conditions, clouds of pure gas could collapse directly under their own gravity, forging a rare, dark matter-free galaxy. This would make it not just an oddity, but a fossil from a different path of cosmic construction, one we never knew existed. The absence of something invisible has never been so loud or so challenging. This profound emptiness sets the stage for the galaxy's third great mystery, one written in the light of its stars. When astronomers analyze that ancient starlight, they find no signature of youth. Every star in NGC 1277 appears to be over 10 billion years old. There is no blue sparkle of hot, newborn suns, no pink glow of stellar nurseries where gas collapses into new generations. This galaxy is a monochrome masterpiece in red and gold, a realm of aging, cooler stars that have been shining since the universe itself was in its adolescence. Astronomers call such places red and dead galaxies, cosmic retirement homes where star formation ceased long ago. But NGC 1277 is the ultimate example, frozen in time so completely it feels less like a retirement and more like a suspension. It is a living fossil, a snapshot of what some of the very first big galaxies looked like, preserved in perfect amber for billions of years. This pristine state is a gift to science. Because no new stars have been born, the galaxy's chemical composition is unchanged. The elements fused in those early stellar furnaces, the primordial mix of hydrogen, helium, and the first traces of heavier metals, remain locked in place. Studying this mix is like unsealing a time capsule from the universe's first few billion years. It tells us about the conditions when these stars were born, how quickly early galaxies enriched themselves with elements, and what the cosmic environment was like before the universe became the busy, star-forming place it is today. This galaxy did not just stop evolving, it chose to become a perfect record of its own dramatic birth. Yet the ancient stars of this fossil galaxy are not alone in their silence. Orbiting this cosmic relic is a tiny, brilliant point of light, a speck of defiance that shines with the power of millions of suns. This is the fourth strange object, an ultra-compact dwarf candidate. To the unaided eye, it would look like a single, unremarkable star lost in the glow of NGC 1277. But its light tells a different story. It is impossibly dense, packing the luminosity of an entire small galaxy into a sphere only about 200 light-years across. If you placed it at the center of our own solar system, its outer edge would only stretch halfway to the nearest star. Within that tiny volume, stars are packed together so tightly that the night sky on a hypothetical planet there would be a perpetual, dazzling noon, with millions of stars closer to each other than we are to our own sun's nearest neighbor. The sheer density creates a gravitational maelstrom, a stellar traffic jam of epic proportions where stars whip around each other at breathtaking speeds. The debate over its true nature is a cosmic detective story. Is it a genuine ultra-compact dwarf galaxy, a rare class of object that is essentially a galaxy stripped down to its bare essentials? Or is it the glittering, exposed heart of a cannibalized galaxy? The theory goes that as NGC 1277 moved through its violent cluster, it may have torn apart a smaller companion galaxy. The process would have shredded away the victim's outer stars, leaving behind only its densely packed core, which now orbits its destroyer like a celestial trophy. There is a third possibility that it is merely a superstar cluster, a single, monstrous burst of star formation from the ancient past, but its extreme brightness and density push it into a mysterious gray area between a large cluster and a small galaxy. This single, brilliant pinpoint forces us to ask, where do we draw the line? When does a cluster of stars become a galaxy? This object, shining with borrowed light from a forgotten cataclysm, holds the answer to a question about identity at the very largest scales. But the echoes of violence are not confined to brilliant trophies. Surrounding NGC 1277, in the deepest, most sensitive images, astronomers have detected something far more subtle and haunting. Faint, arc-like wisps of starlight curl through the darkness like celestial smoke rings. These are tidal streams, the fifth strange object in our list, and they are the ghosts of a forgotten cataclysm. Imagine throwing a handful of glitter into a still pond. The glitter will slowly spread out, tracing the gentle currents and ripples on the water's surface. A tidal stream is the cosmic version of that glitter trail. It is the shredded remains of a smaller star system, a dwarf galaxy or a massive globular cluster that was torn apart by the immense gravity of NGC 1277. As the victim was pulled in, its stars were not instantly consumed. Instead, they were stretched out into long, looping rivers of light that now orbit the larger galaxy, marking the path of their own destruction. Finding these streams is an act of supreme cosmic detective work. It requires peeling back the overwhelming glare of the main galaxy, subtracting its light pixel by pixel, to reveal the faint, gossamer threads that linger at the edge of perception. It is astronomy at its most patient and painstaking. The presence of these tidal ghosts tells a violent story. They are direct evidence that NGC 1277, for all its ancient and pristine appearance, has not been completely isolated. It has fed. It has reached out with its gravitational claws and assimilated other, smaller celestial bodies in its past. This introduces a fascinating contradiction. On one hand, the galaxy's stars are uniformly ancient, suggesting it stopped forming stars itself long ago. On the other, these streams show it was still dynamically active, consuming neighbors to grow in mass, if not in new stars. Yet, the puzzle deepens. Given the galaxy's location in the crowded Perseus cluster, astronomers might expect to see a whole graveyard of such streams, a tangled web of stellar debris from countless close encounters. But the streams around NGC 1277 are few and faint. Their puzzling scarcity suggests a surprisingly lonely existence. Perhaps it has spent most of its cosmic life on a wide, solitary orbit at the fringes of the cluster, only rarely venturing close enough to another galaxy to cause a merger. Or maybe its immense and early growth spurt, which gave it that monstrous central black hole, happened so quickly and so long ago that any evidence of those first, most violent mergers has now completely dissipated, faded into the darkness after 10 billion years. These faint arcs are more than just debris. They are the final, fading testimony of a galactic crime scene, challenging us to piece together a history written in disappearing ink. While the galaxy's ghosts tell stories of ancient collisions, a single star within it writes a different tale, one of a violent escape. This is the sixth strange object, a high-velocity star caught in the act of fleeing. It is not merely moving fast. It is hurtling through the stellar population of NGC 1277 at a speed that defies the gentle gravitational dance of most stars in a galaxy. This star is an outlaw, a cosmic projectile on a one-way trip out of its home. The most likely explanation for its blistering speed is a gravitational slingshot of unimaginable power, originating from the very heart of the galaxy itself. Picture a complex dance of three objects, a stellar binary system, two stars orbiting each other, that wanders too close to the 17 billion solar mass black hole. The immense gravity of the monster can tear the binary apart, capturing one star into a tight orbit while violently flinging the other away at a significant fraction of the speed of light. This ejected star becomes a hypervelocity traveler, a solitary beacon rocketing through the galactic halo and potentially out into the intergalactic void forever. Tracking the trajectory of this star is like following a single piece of shrapnel back to the explosion. By meticulously measuring its path and speed, astronomers can perform a form of cosmic forensics. They can trace its arc backward through time and space, and the point where all those lines converge is the scene of the crime, the precise location and gravitational fingerprint of the supermassive black hole itself. This star is more than a runaway. It is a living probe, a natural experiment sent screaming from the most extreme environment in the galaxy. Its very existence and its flight path confirm the terrifying, active power of that monolithic core, not as a relic of the past, but as a dynamic engine that can still, even in this ancient galaxy, reshape its surroundings with bursts of unimaginable force. The echoes of stellar violence give way to a different kind of witness, one that speaks not of escape but of origins. Orbiting the silent giant is a dense, spherical swarm of ancient stars known as a globular cluster. But this is no ordinary cluster. When astronomers analyzed its starlight, they found a startling chemical signature, a profound lack of the heavier elements astronomers collectively call metals. This cluster is metal poor, forged from material that is almost pristine, the raw hydrogen and helium that filled the cosmos just after the Big Bang. Its stars are the universe's first generation, born from clouds of gas that had never been enriched by the explosive deaths of earlier stars. Finding such a primordial object here is like discovering a cave painting perfectly preserved on the wall of a modern skyscraper. It is a direct, untouched snapshot of the conditions in the very first billion years of cosmic history. The existence of this metal-poor cluster is a cornerstone of evidence for NGC 1277's Relic status. It tells us that this galaxy did not just form its stars early. It did so in one incredibly rapid, intense burst. Think of a brilliant, short-lived firework that uses up all its fuel at once. In that single, furious episode of star formation, every star cluster, including this pristine one, was created. After that, the galaxy simply shut down. No new gas fell in to create younger, metal-rich stars. No major mergers stirred the pot to trigger new rounds of stellar birth. This cluster, with its ancient, pure composition, was locked in place, orbiting unchanged for over 10 billion years while the rest of the universe evolved around it. It is a perfect time capsule, confirming that NGC 1277 is not merely old. It is a preserved specimen from the universe's childhood, a place where time itself seems to have stood still. The pristine stars of that ancient cluster are not the only structures frozen in time. Cutting across the face of NGC 1277 is a faint, lopsided scar, a peculiar lane of dust and gas visible only in the most sensitive infrared and Hubble images. This is the galaxy's asymmetric dust lane, and in a place where symmetry and order are the hallmarks of an old elliptical galaxy, its crooked presence is a glaring anomaly. In a classic spiral galaxy like our Milky Way, dust lanes are elegant, symmetrical features. They trace the inner edges of spiral arms, dark rivers of cosmic soot silhouetted against the brighter starlight behind them, part of a beautiful and balanced structure of rotation and star birth. But here, in this red and dead relic, the dust lane is nothing like that. It is jagged, off-center, and twisted, looking less like a designed feature and more like a wound that never fully healed. This asymmetry is a clue, a signpost pointing to a specific event in the galaxy's long, quiet history. One compelling explanation is a recent minor interaction. Perhaps within the last few 100 million years, a small cloud of gas or a tiny star-poor dwarf galaxy brushed past NGC 1277. The encounter would have been too gentle to trigger any new star formation or to disrupt the orbits of its ancient suns, but it could have been just enough to drag a tendril of dusty material into the galaxy's gravitational field, strewing it into this chaotic, lopsided lane. It would be a cosmic graffiti tag, a fleeting mark left by a passerby. Another possibility looks inward to the galaxy's own strange dynamics. With its missing dark matter halo and its grotesquely overweight central black hole, the gravitational forces at play within NGC 1277 are unlike those in any normal galaxy. This bizarre internal environment could be slowly, over billions of years, warping and twisting any leftover gas and dust into these strange, asymmetric shapes through sheer gravitational stress. But the most poignant interpretation is that this dust represents the last, failed breath of the galaxy itself. This could be the final remnant of the cold gas that once fueled its glorious initial burst of star formation over 10 billion years ago. After that burst, the galaxy was left quenched, its gas either used up or heated so intensely by that early frenzy that it could no longer collapse to form new stars. This dust lane, then, is the cold, dark ashes of that fire, the last bit of raw material that never quite managed to ignite. It is a fossil within a fossil, a silent testament to a process that ended when the universe was young, forever frozen in a lopsided, unfinished state. That faint, lopsided dust lane might be a clue pointing to an even deeper instability. For all its overwhelming mass, the supermassive black hole at the heart of NGC 1277 may not be sitting still. There is a tantalizing, unconfirmed possibility that this gravitational monster is not perfectly centered within its galaxy. It might be off-kilter, wobbling slightly in the void. Pinpointing the exact location of something that emits no light is a feat of extreme precision. Astronomers do not look for the black hole itself, but for the effects of its gravity on the stars whipping around it. They track the motions of these stars at the galaxy's very core, mapping their velocities and orbits with instruments like the Hubble Space Telescope. The center of all these frantic stellar paths should mark the black hole's true position. If that point does not align with the geometric center of the galaxy's starlight, it means the black hole is displaced. The implications of such a discovery would be monumental. A perfectly centered supermassive black hole suggests a stable, settled system. An off-center one is a sign of a recent, violent disturbance. The most likely explanation would be evidence of a past merger where black holes did not fully coalesce. Imagine this scenario. Billions of years ago, NGC 1277 may have cannibalized another galaxy that also contained its own central black hole. As the two galaxies merged, their black holes would have spiraled toward each other, drawn together by gravity and the drag of surrounding stars and gas. They would have danced an immense, slow cosmic waltz, radiating gravitational waves, until they finally collided. But what if that final collision never quite finished? What if, for some reason, the two black holes stalled in their final approach? They could have settled into a binary system, two titans orbiting each other, or one could have been given a gravitational kick that left it oscillating around the true center of mass. A wobbling, off-center behemoth would be the smoking gun for this unfinished act of galactic cannibalism. It would mean the galaxy's most defining feature, its impossible core, might itself be a hybrid, a product of a fusion that was never fully complete. This single, subtle misalignment could rewrite the entire life story of this cosmic fossil, revealing it not as a pristine relic, but as a product of an ancient clash that left a permanent, unstable scar. The possibility of an unstable, wobbling heart makes the galaxy's environment seem even more perilous. Yet against all odds, something fragile persists in its shadow. On the very edge of detection, astronomers have identified a smudge of light, so faint it barely registers against the cosmic background. This is the 10th strange object, an ultra-diffuse satellite candidate. It is the opposite of the brilliant, dense, ultra-compact dwarf we met earlier. This object is a ghost of a galaxy, a vast, wispy cloud of stars stretched so thin that its overall brightness is less than a single % of our own Milky Way. If you could stand within it, the night sky would be almost empty, with lonely stars separated by vast gulfs of darkness. Its existence here is a profound mystery. How can something so delicate survive in the gravitational crossfire of a dense cluster like Perseus, right next to a massive galaxy like NGC 1277? It is like finding a dandelion seed floating, intact, in the middle of a hurricane. The forces at play should have torn it apart long ago. There are two leading theories, and both challenge our understanding. First, it might be a true satellite, bound by gravity to NGC 1277. If so, its survival suggests it is mostly made of dark matter. An immense, invisible halo of dark matter could be acting as a protective shield, its gravity holding the fragile star cloud together against the tidal forces trying to shred it. This would be ironic, as NGC 1277 itself appears to lack dark matter, yet it may host a satellite that is full of it. The second possibility is that it is not a satellite at all, but a background galaxy, billions of light years farther away, that just happens to line up perfectly in our telescope's view. Its ultra-diffuse nature would then be a separate puzzle, but its location would be a cosmic coincidence. Determining the truth requires measuring its distance, one of the hardest tasks in astronomy for such a faint object. If it is a true companion, its fragile state tells a story of incredible quiet. It must be on a wide, stable, and carefully balanced orbit, a cosmic tightrope walk that has lasted for billions of years without a single disruptive encounter. This faint smudge, then, is not just an object. It is a test of stability, a probe of the gravitational landscape around our fossil galaxy, and a question about what can endure in the most violent neighborhoods of the universe. That faint, ghostly satellite is not the only thing that could be warped by the immense gravity of this galaxy. Hidden within the starlight of NGC 1277 might be a secret window to the far edge of the universe. This is the potential for a gravitational lens arc, a cosmic mirage created when the galaxy's total mass acts like a colossal lens in space. The principle is one of Einstein's most famous predictions. A massive object, like a galaxy or a cluster, warps the fabric of space-time around it. When light from a distant background galaxy travels through this warped region, its path is bent, much like light passing through a thick piece of glass. From our viewpoint, the image of that faraway galaxy can be stretched, magnified, and smeared into bright arcs, or even multiple images around the foreground object. Finding such an arc around NGC 1277 would be a discovery of immense power. It would give astronomers a direct, physical tool to weigh the galaxy in a completely independent way. By measuring how severely the background galaxy's light is distorted, scientists could map the total gravitational pull causing that distortion. They could create a precise mass map of everything in NGC 1277, both the stars we see and, crucially, any invisible matter we do not. This would be the ultimate test for the galaxy's missing dark matter. If the lensing arc shows a mass that matches only the visible stars and that monstrous black hole, it would be definitive proof that the dark matter halo is truly absent. If, however, the lensing reveals more mass than we can account for, it would mean the dark matter is there after all, but in a form or distribution so strange that it has eluded every other method of detection. Observing this effect is a monumental challenge. The lensing signal would be incredibly subtle because NGC 1277, while massive, is a single galaxy, not a dense cluster which produces the most dramatic arcs. It would be like trying to detect the bend in a light ray passing through a single, perfectly polished marble, rather than a giant magnifying glass. It requires exquisitely sharp, deep images and a fortunate cosmic alignment, where a perfectly positioned background galaxy lies directly behind the fossil galaxy's mass. The hunt for this faint, curved scar of light is more than a search for another object. It is a pursuit of pure measurement, a chance to use the universe itself as a scale to weigh one of its most mysterious inhabitants. The search for a gravitational lens is a search for light bent by immense mass, but sometimes the most telling clue is an absence of light itself. This brings us to the 12th strange object, the X-ray quiet nucleus of NGC 1277. At the galaxy's heart, where its 17 billion solar mass black hole resides, astronomers expected to find a roaring cosmic furnace. Typically, a black hole of that size, even if not in a bright quasar phase, should be pulling in stray gas and dust from its surroundings. As this material spirals inward at nearly the speed of light, it compresses and heats to millions of degrees, glowing fiercely in high-energy X-rays before vanishing past the event horizon. This X-ray signature is a universal beacon for supermassive black holes. Yet when telescopes like Chandra turned their gaze to the core of this fossil galaxy, they found a profound and puzzling silence. The center is dark in X-rays. It is not just quiet, it is eerily, unnervingly dormant. This presents a stark contradiction, a gravitational monster of unimaginable appetite, sitting in absolute stillness. Why is it not feeding? The most direct answer paints a picture of extreme cosmic isolation. NGC 1277 may have starved its own heart. Recall its ancient red stars and that lopsided dust lane of cold ashes. The galaxy appears to have exhausted or expelled all of the cold, dense gas required to fuel a black hole's accretion disk billions of years ago. The environment around the black hole is not just empty, it is a perfect vacuum on a galactic scale. There is simply nothing left for it to consume. It is a starved giant in a galactic desert, a king with an immense throne but no kingdom left to rule. This starvation could be a direct consequence of the galaxy's violent youth. That initial, furious burst of star formation that created all its ancient suns may have used up the gas reserves in one go. Alternatively, the sheer energy output from that young, feeding black hole itself back when it might have been a brilliant quasar, could have blown the remaining gas clean out of the galaxy, shutting down both star formation and its own future food supply in a single self-destructive act. This leaves us with a haunting image. The most disproportionately massive black hole ever discovered is now a dormant relic, a sleeping titan trapped in a tomb of its own making, surrounded by the ancient stars it helped create and then starve. Its silence is not a sign of weakness, but the final, quiet evidence of a cataclysm that ended over 10 billion years ago. This profound silence at the galaxy's heart makes the motion of its stars even more telling. Deep within NGC 1277, astronomers have detected a subtle but significant clue written in the orbits of its ancient suns. The inner core of stars, those closest to the supermassive black hole, appear to be spinning on a different plane or even in a different direction compared to the stars in the galaxy's outer regions. This is called a kinematically decoupled core, and it is the fossilized signature of a galactic collision frozen in time. Imagine two massive whirlpools in a cosmic ocean, each spinning with its own distinct rotation. Now, picture them slowly merging into one larger whirlpool. The water from each original vortex does not instantly forget its original motion. For a long time, perhaps forever, the inner heart of the new, combined whirlpool might retain a twist, a different spin direction from the outer layers. That is precisely what we may be seeing in this fossil galaxy. The stars in the inner core could be the surviving population from one of the original galaxies that merged to form NGC 1277, preserving their original orbital dance even as the outer stars settled into a new, unified motion from the other galaxy. This decoupling is not something you can see in a static image. It requires painstaking measurements of starlight, using a technique called spectroscopy to map whether stars are moving toward us or away from us at every point across the galaxy's face. By building a detailed velocity map, astronomers can reconstruct the complex ballet of stellar orbits. Finding a distinct spin axis in the core is like discovering a sealed chamber inside a building that still spins on its original ancient foundation, while the rest of the structure has settled on a new one. This evidence points directly to a major merger in the galaxy's distant past, likely the very event that created its monstrous central black hole, and perhaps even contributed to its strange, dark matter-free state. It suggests that NGC 1277 is not a simple, pristine relic that formed in isolation, but a hybrid, a product of a violent union whose final, uneasy truce is still evident in the contradictory motions of its stars billions of years later. Amidst the uniform ancient stars, a delicate bubble of light tells a different story. This is a planetary nebula, the final, beautiful sigh of a dying sun. In its last stages, a star like our own will puff off its outer layers into space, creating a glowing, often spherical shell lit by the intense ultraviolet radiation from its exposed, hot core. Within NGC 1277, one such nebula has been found, and its light carries a chemical message from a bygone era. When astronomers analyze its spectrum, they find peculiar ratios of elements, specifically an overabundance of nitrogen and helium relative to oxygen. This is not a random mixture. It is a specific fingerprint left by the life and death of the star that created it. Stars act as cosmic forges, fusing lighter elements into heavier ones in their cores. A star's mass determines its fate and the cocktail of elements it releases. The unusual chemistry in this nebula suggests its progenitor star was born with a specific high mass and evolved in a very particular way, enriching its outer layers with the products of internal nuclear fusion before casting them off. The high nitrogen, in particular, is a clue. It points to a process where the star dredged up material from deep within its core, material that had been processed through the carbon-nitrogen-oxygen cycle, a chain of nuclear reactions that favors producing nitrogen. This only happens efficiently in stars of a certain mass and evolutionary path, but the story gets deeper. This chemical fingerprint is also a probe of the galaxy's primordial environment. The star that created this nebula was born over 10 billion years ago from the raw gas of the young NGC 1277. The elements we see in the nebula today are a combination of the original elements present in that birth cloud and the new elements the star forged itself. The peculiar ratios suggest the star was born from gas that was already slightly enriched with the products of even earlier generations of massive stars. Stars that lived fast, died young in supernova explosions, and seeded the galaxy with their own unique elemental signatures. This single, glowing shell is therefore a double record. It tells the life story of an individual, long-dead star, and it also preserves a sample of the chemical conditions in this fossil galaxy during its brief, intense period of star formation. It is a time capsule within a time capsule, a chemical fossil that lets us test our models of how the very first stars lived, died, and prepared the universe for everything that came after. While the chemical whispers of that ancient nebula tell a story of stellar life and death, a far more violent gravitational secret may be hiding in plain sight. Tucked away within one of the ancient globular clusters orbiting NGC 1277, astronomers are hunting for a phantom of a different scale. This is the candidate intermediate mass black hole, a cosmic missing link with a mass of a few thousand suns. It represents a class of object that has long been theorized, but remains incredibly elusive, a ghost in the machine of cosmic evolution. We know of stellar mass black holes, the collapsed cores of massive stars, weighing up to a few dozen solar masses. And we know of the supermassive behemoths, like the one at the galaxy's heart, weighing millions or billions of suns. But the vast gulf between these two extremes has been a persistent mystery. How does a universe get from a small, stellar corpse to a gravitational monster that can dominate an entire galaxy? The answer may lie in these intermediate mass black holes, and NGC 1277's pristine environment offers a perfect hunting ground. To find one, astronomers perform a meticulous stellar census within a globular cluster. They use the Hubble Space Telescope to track the motions of hundreds of individual stars over years, mapping their precise orbits. The goal is to spot a telltale sign of an unseen anchor. If the stars at the very center of the cluster are whipping around at unexpectedly high speeds, swirling as if caught in an invisible whirlpool, it points to a concentrated mass holding them there. That mass, too small to be a dense knot of stars and too large to be anything else, would be the signature of an intermediate mass black hole. It is detective work on a cosmic scale, measuring the silent tug of darkness on pinpricks of light. The implications of finding such an object here are profound. It could be a preserved seed, a direct fossil from the universe's first chapter. One leading theory for how supermassive black holes grew so big so fast is that they started from these intermediate mass seeds, formed in the dense environments of the earliest star clusters. If one is found orbiting this fossil galaxy, it would be like discovering a sapling from the same ancient forest that grew the galactic redwood at its center. It offers a potential clue to the origin of the impossible core itself, suggesting its growth may have begun not from a single stellar collapse, but from the merger of many of these mid-sized seeds in the violent, crowded nursery of the young universe. This silent hunter, if it exists, is more than just another strange object. It is a potential key to understanding the very first steps on the path to building a cosmic giant. The silent heart of this fossil galaxy may have left a permanent scar on the cosmos. If the supermassive black hole was ever an active quasar, its fury would have shot twin beams of plasma traveling at nearly the speed of light far out into intergalactic space. These beams, glowing fiercely in radio waves, would have carved out colossal cavities in the thin gas between galaxies. Over millions of years, as the black hole's engine shut down, those beams would have faded. But the giant, bubble-like lobes they inflated might still linger, a faint radio whisper against the silent dark. These are ghost jets, the fossilized remnants of a roar from an era long past. Finding them requires tuning our most sensitive radio telescopes, like the Very Large Array, to listen for this ancient echo. They would not look like sharp beams, but rather as two vast, diffuse, and symmetrical clouds of radio emission, stretching far beyond the visible starlight of NGC 1277. Like the fading smoke rings from a cosmic cannon fired eons ago. Their detection would be a revelation. It would confirm that the galaxy's monstrous heart was not always dormant. It would tell us exactly when, in the deep past, this black hole last feasted. By measuring the size of the lobes and the speed at which such structures typically expand, astronomers could essentially carbon date the last major outburst. More importantly, the shape and condition of these fossil lobes would reveal the nature of that final meal. Were the jets powerful and straight, punching cleanly through the galaxy's halo, or were they weak and disrupted, choked off by a lack of fuel or by the strange internal dynamics of this dark matter-free environment? These ghostly structures would act as a fossilized energy budget, showing us how much power the black hole injected into its surroundings before it starved. This could solve a key mystery. Did that final, furious outburst help clear out the remaining gas, permanently quenching star formation and leaving the galaxy red and dead? The search for these radio ghosts is a search for the last gasp of a cosmic giant, a final piece of evidence that could explain why this galaxy looks so perfectly, so eerily preserved. The search for ghostly jets reveals an environment of profound stillness, but within the ancient stellar swarms orbiting this galaxy, a different kind of defiance shines. Scattered among the old, red stars of its globular clusters are points of unexpected blue light. These are blue stragglers, stars that burn hotter, brighter, and bluer than any of their neighbors, appearing as youthful interlopers in a retirement home for suns. Their very existence in a 10-billion-year-old cluster is a paradox. All the stars in these clusters were born at roughly the same time from the same primordial gas cloud. By now, every massive star should have long since burned out, leaving behind only cooler, redder, lower-mass stars. The blue stragglers break this rule, shining with the vigor of stars only a fraction of their true age. They are not actually young, but stellar imposters, born from violence. In the densely packed core of a globular cluster, stars are crammed together so tightly that close encounters and direct collisions are not just possible, they are inevitable over billions of years. A blue straggler is most often the product of such a cosmic crash. Two older, lower-mass stars can collide and merge, pooling their fuel to create a single, more massive, hotter, and bluer star, essentially hitting the reset button on its life cycle. Alternatively, one star in a tight binary system can siphon gas from its companion, feeding itself until it grows more massive and reignites with a hotter, bluer flame. The prevalence of these blue stragglers in the clusters around NGC 1277 is a direct measurement of past density. It tells astronomers that these clusters were once even more densely packed than they are today. Every blue straggler we see is a fossilized record of a stellar traffic jam, a moment where two stars drew too close and became one. Their numbers give us a clock of sorts, not of time, but of crowding. A cluster with many blue stragglers was, in its youth, a place of frantic, close-quarters stellar dances. This reinforces the image of NGC 1277's early environment as one of extreme intensity, where not only did stars form in a furious burst, but they were then packed into dense clusters where they continued to interact, merge, and transform long after their birth. These brilliant blue points are not mistakes in the fossil record. They are the stress fractures within it, showing us the tremendous pressures that shaped this galaxy's first and only generation of stars. The brilliant blue stragglers reveal a history of intense crowding, but if we pull our view all the way back, a very different kind of emptiness emerges. NGC 1277 is a galaxy stripped bare. Unlike every other galaxy of comparable size, it lacks the vast, faint, and sprawling stellar halo that should envelop it like a ghostly shroud. This missing halo is the 18th strange object, and its absence is a profound clue to this fossil's solitary life. A stellar halo is the galactic equivalent of an archaeological dig site. It is built over billions of years, primarily from the torn-apart remains of smaller satellite galaxies that were cannibalized by the larger one. Each act of galactic consumption leaves behind streams and clusters of stars that eventually mix into a diffuse, spherical cloud surrounding the main galaxy. Our own Milky Way has a majestic, ancient halo, filled with some of the oldest stars in the universe and punctuated by the lingering cores of dwarf galaxies it consumed. For NGC 1277 to have almost none of this structure means its history has been one of incredible isolation. It did not grow by steadily eating its neighbors. This supports the idea that it formed in one rapid, monolithic collapse of gas very early in cosmic time, essentially being born almost fully formed. After that initial burst, it must have lived on a quiet, lonely orbit, avoiding the gravitational interactions that would have decorated it with a halo of stellar debris. Think of it as a cosmic hermit. While other galaxies were out in the universe socializing, merging, and accumulating the stellar equivalent of souvenirs and scars, this one stayed apart. It is a naked galaxy, showing us only its original, ancient form without the layered history of acquisitions that clothe its peers. This bareness makes it a uniquely pure laboratory. Without a complex halo to confuse the picture, the light we see comes almost exclusively from that first, pristine generation of stars. It is a direct, unedited look at the product of the universe's earliest and most intense period of galaxy building, a solitary giant that has kept to itself for over 10 billion years. The galaxy's stark isolation may have left its internal forces frozen in a unique state. Deep within the ancient light of NGC 1277, astronomers might find a hidden signature of order, a magnetic field anomaly. This invisible structure is not something we can photograph directly. Instead, it reveals itself through a subtle property of light called polarization. As starlight or the faint glow from dust travels through space, it can become polarized, meaning its light waves are aligned in a specific direction. This alignment often happens when the light passes through clouds of dust grains that are themselves oriented by a magnetic field, like iron filings lining up around a magnet. By carefully measuring the polarization of light coming from different parts of the fossil galaxy, we could map the shape and strength of its magnetic field. The results could be startling. In a normal spiral galaxy, magnetic fields are often ordered along the spiral arms, shaped by the rotation and constant churn of star formation. But in this red and dead relic, where rotation and new stars ceased billions of years ago, what would its magnetic field look like? One possibility is a field that is incredibly ordered and strong, a fossilized imprint from its violent youth. During that initial, furious burst of star formation, supernova explosions and stellar winds could have generated a powerful, large-scale magnetic field that was then locked in place as the galaxy quenched. With no subsequent turbulence to tangle or weaken it, this primordial field might have persisted, perfectly preserved like a fly in amber. Alternatively, the field could be weak and chaotic, or even aligned in a bizarre, lopsided configuration, twisted by that off-center black hole or the galaxy's strange internal dynamics. The implications are profound. A strong, ordered magnetic field in the early galaxy could have acted as a cosmic regulator. Magnetic fields provide pressure and can channel flows of gas. A powerful field might have helped funnel gas efficiently into the core, feeding both the rapid star formation and the growth of the monstrous black hole in one coordinated frenzy. Conversely, it could have also acted as a barrier, preventing gas from collapsing into new stars too quickly, or even helping to launch powerful outflows that expelled gas and shut down the galaxy's future. This invisible architecture, if we can detect it, would be a direct line back to the forces that shaped the galaxy's single defining event. It is the hidden blueprint of its creation, a whisper of the pressures and fields that guided its birth and then left it perfectly, eerily still. That hidden magnetic blueprint could have guided the final, violent act of a galactic feast. Orbiting the silent black hole at the heart of NGC 1277, astronomers are hunting for a structure that should not exist. It is the potential tilted nuclear disk, a tiny, separate whirlpool of stars or gas spinning on its own defiant axis. Picture a vinyl record spinning on a turntable. Now imagine placing a second, much smaller record directly on top of it, but tilted at a sharp 45-degree angle. Both are spinning, but their planes of rotation are completely misaligned. That is the kind of cosmic geometry we are talking about here, but on a scale of light years. In a settled, ancient galaxy, everything should have settled into a single, orderly plane of rotation, like all the planets in our solar system orbiting in roughly the same flat disk. A steeply tilted inner disk is a sign of a recent and violent intrusion. The most likely origin story is a tale of cosmic cannibalism. Billions of years after its main formation, a small, gas-rich dwarf galaxy may have wandered too close to NGC 1277. As it was torn apart by tidal forces, a stream of its gas would have been funneled toward the supermassive black hole. But this gas would not have arrived with the same orientation as the galaxy's existing stars. It would have carried the orbital signature of its original home. As this captured material spiraled inward, it would have formed a new small accretion disk or a tightly wound ring of stars, stubbornly maintaining its original tilted angle relative to the main galaxy's spin. Detecting this structure is a monumental challenge in precision. You cannot see it in a direct image. Instead, astronomers must use a technique called integral field spectroscopy. They take the light from the galaxy's very core and spread it out into a spectrum for every single pixel, creating a three-dimensional data cube, 2 dimensions of space, and 1 of wavelength. Within this cube, they can map the velocity of the gas or stars in exquisite detail. The signature of a tilted disk would be a distinct rotating pattern. On one side of the black hole, the material in the disk would be moving toward us at high speed, showing a blue shift in its light. On the exact opposite side, it would be moving away at the same speed, showing a redshift. But this pattern would be tilted relative to the rotation axis of the outer galaxy, a clear signal of a separate, misaligned structure dancing around the central darkness. Finding this tilted whisper would be a direct confirmation that the fossil galaxy's quiet exterior hides a more complex digestive history. It would prove that even after its main star-forming life ended, it was still capable of consuming smaller systems, and that the final remnants of those meals are still swirling, out of sync, around its monstrous heart. Amidst the sea of ancient suns, one burns with a peculiar and fiery glow. This hyper-luminous red giant is a stellar anomaly, a single point of light that outshines its neighbors with a deep ruby hue. In a galaxy where most stars are old and stable, this one is in the throes of a dramatic and short-lived transformation. It is far brighter and redder than a typical red giant, the final phase for stars like our Sun. This suggests we are witnessing something far more extreme, a star caught in a brief and violent window of its life. One possibility is that it is a super-asymptotic giant branch star, a rare and final evolutionary stage for stars with masses between about 8 and 10 times that of our Sun. These stars are cosmic pressure cookers. They have exhausted the hydrogen and helium fuel in their cores and are now fusing heavier elements in shells around a dense carbon-oxygen core. This process is unstable and spectacular. The star swells to a monstrous size, becoming incredibly luminous and blowing off its outer layers in powerful, pulsating winds. It is a prelude to a specific kind of cosmic death, one that leaves behind a dense stellar remnant called a white dwarf. But there is another, equally fascinating explanation. This brilliant red beacon might not be a single star at all, but a massive, younger star shrouded in a thick cocoon of its own making. Imagine a brilliant blue star, many times more massive than our Sun, buried within a vast cloud of dust and gas it has ejected. The visible light from the hot star is absorbed by this dusty shroud, which then re-radiates the energy as intense infrared and red light. From our distant viewpoint, it appears as a single, impossibly bright red orb. This would make it a stellar factory in disguise, a place where conditions might be right to form new planets or even trigger secondary star formation, all hidden behind a veil of cosmic soot. The extreme properties of this star, whichever explanation is true, make it a unique probe. Its light carries the chemical signature of the ancient, metal-rich environment of NGC 1277. By studying its spectrum, astronomers can measure the precise abundance of elements like carbon, nitrogen, and oxygen in its atmosphere. These ratios are a direct test of our models of how stars of different masses evolve in such a primordial setting. They tell us how nuclear fusion proceeds in the hearts of these giants, and how efficiently they pollute the surrounding space with new elements. This one's strange, crimson sun is a laboratory in the sky, a fleeting natural experiment that lets us watch the final acts of stellar life play out under conditions that have been frozen in time for over 10 billion years. That crimson giant's final act is a testament to stellar chemistry, but a far more energetic signature might be hiding just beyond the visible spectrum. On the very edge of detection, a faint, high-energy whisper could be associated with this fossil galaxy. This is the potential gamma-ray source, a trace of the most violent processes in the universe, captured by instruments like the Fermi Gamma-Ray Space Telescope. Gamma rays are not light as we know it. They are the most energetic form of electromagnetic radiation, billions of times more powerful than visible light. They are the signature of cosmic catastrophes, the death cries of massive stars, the screams of matter falling into black holes, or the silent annihilation of exotic particles. Finding even a faint, unresolved blip of gamma rays that coincides with the exact position of NGC 1277 would be a monumental, if speculative, discovery. It would force us to consider two radical possibilities, each more thrilling than the last. The first is a whisper from the invisible. One of the leading candidates for dark matter is a hypothetical particle called a weakly interacting massive particle. When two of these particles collide, according to some theories, they can annihilate each other in a flash of energy, producing gamma rays as a byproduct. If the missing dark matter around NGC 1277 is not missing at all, but is instead in a form that does not interact like normal dark matter halos, this annihilation could produce a faint, diffuse glow in gamma rays. Detecting such a signal would be a direct, tangible clue to the identity of the universe's most elusive substance, coming from a place where its gravitational absence has been so puzzling. The second possibility is a roar from the silent giant. Our dormant black hole, starved of gas, might not be completely dead. Even in its quiescent state, stray particles or the occasional shredded star could still spiral in. In rare, chaotic moments, this trickle of material could trigger a sudden, violent flare, a brief resurgence of activity where particles are accelerated to near light speed and slam into the surrounding environment, producing a short-lived burst of high-energy gamma radiation. It would be the final, faint heartbeat of a monster in a deep coma, a single pulse proving that the engine, though cold, is not entirely shut down. Hunting for this signal is a needle in a haystack search across the entire sky. The Fermi telescope's data is a map of countless gamma ray sources, from distant blazars to pulsars in our own galaxy. Isolating a faint, steady glow or a single, rare flash that aligns perfectly with this distant fossil requires meticulous statistical analysis and a significant dose of cosmic luck. But the potential reward is a new window into the most extreme physics, offering either a clue to the nature of dark matter or a glimpse of the last gasps of the most impossibly proportioned black hole we have ever found. Deep within the gamma-ray silence, another visual trickery challenges our perception. At the very heart of NGC 1277, high-resolution images sometimes reveal a puzzling sight: two distinct, bright knots of light where only one supermassive black hole should reside. This is the double nucleus illusion, a cosmic mirage that forces astronomers to question what their eyes are telling them. The first and most likely explanation is a simple yet profound coincidence of perspective. A foreground star, one that belongs to our own Milky Way galaxy and just happens to lie directly along our line of sight, could be superimposing its pinpoint brilliance over the galaxy's true core. From our distant vantage point billions of light years away, the two unrelated sources of light merge into what appears to be a double structure. It is the ultimate cosmic photobomb, a stellar bystander from our own galactic neighborhood, accidentally stepping into the frame of one of the universe's most distant mysteries. A second possibility is that one of the knots is not a single star, but an incredibly dense star cluster orbiting perilously close to the black hole. In the violent gravitational tides near the galaxy's center, such a cluster could be compressed to an extreme density, shining with the combined light of millions of stars packed into a tiny volume, creating a second, brilliant point that rivals the glow of the galactic core itself. But the most tantalizing explanation involves time, not space. One of those bright knots could be a light echo. Imagine the black hole in its distant past, letting out a final, brilliant flash of light as it swallowed a star or experienced a sudden surge of accretion. That flash would have exploded outward at the speed of light. Some of that light traveled directly to us, and we saw it as a historical event long ago. But some of that light may have hit a vast, intervening cloud of dust or gas hovering around the core. That cloud would have absorbed the flash and then re-emitted it, like a cosmic mirror, but with a delay. The re-emitted light, traveling a longer path, would only be reaching our telescopes now, creating a faint, secondary ghost image of that ancient eruption, displaced slightly from the true center. Distinguishing between these possibilities is not just an exercise in cleaning up an image. It is fundamental to mapping the true terrain of the galactic core. If the double nucleus is real and not an illusion, if there are two massive, bright objects at the center, it would be evidence for an ongoing merger of two supermassive black holes, a discovery that would shake our understanding of the galaxy's quiet present. Unraveling this illusion requires the ultimate in observational precision. Astronomers must take multiple images over years, watching for movement. A foreground Milky Way star will gradually shift its position relative to the fixed background of the distant galaxy. A dense star cluster will move as well, but in a slow, predictable orbit around the central black hole. A light echo, however, would remain static, but might change in brightness or color over time as the echo propagates through different parts of the dust cloud. Each observation peels back a layer of the illusion, bringing us closer to the solitary, silent truth at the center of this ancient fossil. A repeating crackle of cosmic static might be broadcasting from the direction of this silent fossil. Fast radio bursts are the universe's most enigmatic signals, fleeting blasts of radio waves that pack the energy of 500 suns into a few milliseconds. Most appear once and vanish forever, but a handful are known to repeat, firing off again and again from the same patch of sky. The wild speculation is this: what if one of these known repeating sources is not in a distant, star-forming dwarf galaxy as we suspect, but is instead associated with the ancient, red and dead realm of NGC 1277? The idea is thrilling because it defies everything we think we know about where these bursts come from. The leading theories for repeating fast radio bursts involve highly magnetized, spinning neutron stars called magnetars. These are the collapsed cores of massive stars that lived fast and died young, requiring a recent supernova and a population of young, massive stars to create them. NGC 1277, with its 10-billion-year-old stellar population, should have no such young magnetars. Its last massive star died when the universe was a fraction of its current age. So if a repeater were somehow linked to this galaxy, it would force a complete rethink of the engine behind these signals. Perhaps the source is something even more exotic that can persist in a quiescent galaxy, a long-lived, highly magnetized white dwarf, or a bizarre interaction between that monstrous black hole and a dense, ancient neutron star in a decaying orbit. The implications would ripple far beyond a single mystery. It would suggest that the conditions for producing these brilliant radio flashes are not exclusive to the vibrant stellar nurseries of young galaxies. They could also spark to life in the deepest quiet of the cosmos, in places where time itself seems to have stopped. Finding such a link is a needle in a cosmic haystack, requiring painstaking analysis to see if the precise coordinates of a repeater align with this distant galaxy. But the mere possibility opens a door to a universe where the most violent, energetic signals might echo from its oldest, most silent tombs. The silence of that fossil galaxy is not absolute. It resonates on a frequency no human ear can hear. The monstrous black hole at the heart of NGC 1277, especially if it was forged in an ancient collision, is likely contributing to a cosmic hum that permeates the entire universe. This is the stochastic gravitational wave background, a sea of ripples in the fabric of space-time itself, and this distant relic is one of countless drums beating in that silent choir. Imagine the universe is a vast, still pond. Each merging supermassive black hole pair is like a pebble dropped into that pond. The splash creates ripples that travel outward. Now, imagine not one pebble, but millions, dropped at different times and places across the entire pond. The ripples from all those splashes would crisscross, overlap, and merge into a constant, chaotic churn of the water's surface. That churn is the gravitational wave background, a collective hum of every massive black hole merger that has ever occurred throughout cosmic history. The behemoth in NGC 1277, with its 17 billion solar masses, is a prime suspect for having been involved in one of the loudest splashes of all. If its impossible size is indeed the product of a past merger, that collision would have been a cataclysmic event, shaking the very foundations of space-time with waves of unimaginable power. The energy released in the final seconds of such a merger would have briefly outshone the light of every star in the observable universe combined. That specific event is long over, its direct wave train lost in the abyss of time and distance. But its echo is not gone. It has joined the chorus. Scientists detect this background hum not with telescopes, but with celestial metronomes called pulsars. These are rapidly spinning neutron stars that beam radio waves toward Earth with the precision of atomic clocks. As gravitational waves from the background hum wash over our galaxy, they minutely stretch and squeeze the space between us and these pulsars, causing their rhythmic ticks to arrive a few billionths of a second early or late. By monitoring an array of these pulsars across the sky for decades, projects like the North American Nanohertz Observatory for Gravitational Waves have begun to hear this faint, all-pervasive rumble. It is the sound of the universe's history of violence, a fossilized record of cosmic collisions written not in light, but in the warping of space itself. The Relic black hole in NGC 1277, silent and starved today, is therefore still speaking. Its past fury is encoded in that universal hum, a single, deep note in a symphony composed by every giant that ever merged. This transforms our view of the fossil from a static portrait into an active participant in the universe's deepest, most fundamental rhythm. The cosmic hum of ancient mergers creates more than just waves, it sends out refugees. Drifting through the immense voids between galaxies in the Perseus cluster are solitary stars, cast out from their homes by gravitational violence. These are intergalactic stars, and NGC 1277 might be slowly, silently stealing them. This fossil galaxy, for all its isolation, is not floating in a perfect vacuum. It moves through a sea of these stellar orphans, and its immense gravity acts like a net, capturing them one by one. This process would add a subtle, almost invisible layer of contamination to its pristine stellar population. Imagine a museum of ancient artifacts, each one carefully cataloged and dated. Now imagine a curator, over centuries, secretly adding a single modern coin to a display case every few years. The overall collection still looks ancient, but a forensic examination would reveal these subtle, out-of-place additions. NGC 1277 could be that museum, and the intergalactic stars are those modern coins. Identifying these stellar thieves is a task of extreme precision. Astronomers must measure the velocity of individual stars within the galaxy's halo with incredible accuracy. An intergalactic capture would leave a clear signature. These stars would not be orbiting in the same organized way as the galaxy's native-born population. Instead, they would be moving on wild, hyperbolic trajectories, with speeds and directions that do not fit the smooth gravitational flow of the galaxy. They are cosmic hitchhikers, still carrying the momentum of their violent ejection from their original homes. Finding even a handful of such stars would rewrite the narrative of the galaxy's quiet history. It would prove that NGC 1277, while not merging with other galaxies, is still interacting with its environment in a slow, patient act of accumulation. Each captured star is a fossilized piece of evidence from a different galactic crime seen elsewhere in the cluster, a silent witness to a collision that happened far away, now brought into the gravitational fold of this ancient relic. This adds a profound layer of complexity to the idea of a pristine fossil. It suggests that even the most isolated giants are not completely closed systems. They are participants in a slower, more subtle form of cosmic exchange, building their populations not through grand mergers, but through the steady accretion of stellar dust. Even the captured starlight might be hiding a deeper darkness. Among the ancient globular clusters orbiting this fossil galaxy, one could stand apart, not for its brilliance, but for its profound gravitational shadow. This is the dark globular cluster, a spherical swarm of stars that feels far heavier than it looks. Its visible light tells one story, a modest tale of a few 100,000 ancient suns. But the motion of those stars tells a completely different, more unsettling one. When astronomers measure how fast the stars are whipping around inside the cluster, they find speeds that are simply too high. The combined gravity of all the visible stars is not enough to hold this frantic stellar dance together. The cluster should have flown apart eons ago. The only explanation is that there is extra mass in there, a lot of it, mass that we cannot see. This is the signature of dark matter, but in a place where it has no right to be. Standard globular clusters are thought to be almost devoid of dark matter. They are believed to form from the collapse of a single giant cloud of gas within a larger galaxy, a process that efficiently sheds dark matter. Finding a cluster bulging with it would turn that idea on its head. It would suggest this object might not be a true globular cluster at all, but the stripped-down core of an entire dwarf galaxy that NGC 1277 cannibalized long ago. A dwarf galaxy's core is rich with dark matter, and if the outer stars were torn away, the dense, dark matter-rich heart could remain, masquerading as a simple star cluster. There is another, even more extreme possibility. What if the invisible mass isn't dark matter, but a graveyard? This cluster could be packed with the corpses of dead stars, black holes, and neutron stars, left behind after the most massive members of the cluster ended their lives in supernova. Over billions of years, these heavy remnants would have sunk to the cluster's center through gravitational interactions, creating an invisible, dense knot of dark mass that now governs the orbits of the living stars. This would mean we are looking at a stellar retirement home where the retirees, silent and dark, vastly outnumber and outweigh the few living residents. Discovering such an object would force a rewrite of the life cycle of star clusters in environments like this fossil galaxy. It would reveal that the quiet, ancient exterior of NGC 1277 might hide a core of incredible gravitational density, not just in its central black hole, but scattered throughout its retinue of ancient companions. A faint, warm glow blooms in the darkness, a smudge of heat invisible to our eyes. In the crisp, cold starlight of this ancient galaxy, one small region betrays a secret warmth, shining with a distinct orange hue in the mid-infrared part of the spectrum. This infrared excess blob is a thermal anomaly, a pocket of dust heated to temperatures far above the frigid background of interstellar space. Its presence in a galaxy that stopped forming stars over 10 billion years ago is a puzzle wrapped in warmth. What could possibly be generating this heat in a place so profoundly cold and still? The first possibility is a hidden nursery. Despite the galaxy's red and dead reputation, this blob could be a tiny, localized pocket of clandestine star birth. Imagine a last, forgotten wisp of cold gas, somehow shielded from the galaxy-wide quenching, that has only recently begun to collapse under its own gravity. Within this dusty cocoon, new stars could be igniting, their brilliant ultraviolet light absorbed by the surrounding dust, and re-radiated as the gentle, warm glow we detect. It would be a cosmic afterthought, a single late-blooming flower in a fossilized garden. A second, more intimate explanation points to a single, aging star. This warm glow could be the signature of a colossal debris disk, a vast ring of rocky and icy rubble encircling an old sun. Similar to our own solar system's Kuiper belt, but on a monstrous scale, this disk would be the leftover construction material from the star's planetary system, now stirred up by gravitational interactions or collisions. The dust grains, warmed by the star's faint light, would emit the infrared signature we see. This would be a remarkable discovery, evidence that planet formation, a process we associate with youthful, gas-rich galaxies, might have also occurred in this ancient relic, leaving behind dusty graveyards of failed worlds. But the most dramatic possibility ties the heat directly to the galaxy's silent giant. This warm dust could be the aftermath of a recent micro-event near the supermassive black hole. A small asteroid, a wandering planet, or even a brown dwarf star that ventured too close could have been torn apart by the black hole's tidal forces in a relatively minor disruption. The shredded debris, swirling into a temporary hot accretion disk, would have heated the surrounding dust to incandescence before fading away. This blob would then be the fading ember of a small, recent snack for the dormant monster, proving that even in its starved state, it can still occasionally stir. Each explanation paints a different portrait of the galaxy's present. Is it secretly fertile, still capable of creating new suns? Is it dotted with the architectural ruins of ancient planetary systems? Or is its heart still faintly warm, occasionally rumbling with the digestion of cosmic crumbs? This one warm spot is a thermometer, measuring a hidden activity we never expected to find. The warmth of that single infrared blob hints at a galaxy-wide ocean of invisible energy. Beyond any isolated point of heat, the entire interstellar space within NGC 1277 is filled with a thin, searing wind. This is the collective breath of its ancient giants, a supersonic stellar wind that has been blowing for over 10 billion years. In their final, expansive phases, the galaxy's old red giant and asymptotic giant branch stars do not die quietly. They exhale. Each one drives a powerful wind, ejecting its outer layers into space at speeds that can exceed hundreds of thousands of kilometers per hour. Multiply that by millions of such stars, all contributing their spent fuel to the void, and you create a pervasive, hot interstellar medium. This is not the cold, dense gas of a star-forming nursery. It is a tenuous, million-degree plasma, a thin soup of ionized atoms whizzing through the gaps between stars. Detecting this medium requires looking for the faint, specific fingerprints of highly ionized elements like oxygen-6 and neon-5 in the galaxy's ultraviolet spectrum. These ions can only exist in an environment bathed in intense heat or extreme ultraviolet radiation. Finding them confirms that the space between the stars is not empty, but simmering. The kinematics of this gas are a historical record. By measuring its temperature and its motion, whether it is flowing out of the galaxy, swirling in some pattern, or sitting in a turbulent equilibrium, astronomers can perform a form of cosmic accounting. They can calculate the total energy that has been pumped into this medium over the galaxy's entire lifetime. Every stellar wind, every supernova shock wave from the ancient past has deposited energy into this reservoir. The current state of the gas tells us if that energy input was a single, furious burst that has since cooled, or a steady, simmering output that has maintained the heat. In a fossil galaxy like this one, the answer is crucial. It helps explain why no new stars have formed. For cold, dense clouds to collapse and birth new suns, they need to radiate away their heat and turbulence. A hot, high-pressure interstellar medium acts like a cosmic pressure cooker lid. It prevents any remaining cool gas from condensing, and it can even evaporate existing clouds. The supersonic winds from those ancient stars, therefore, may have been the very mechanism that sealed the galaxy's fate. Their collective, endless breath did not just fill the space between stars. It may have created a permanent, hostile environment that guaranteed the galaxy's quiet, red, and dead future, locking its story in a state of heated suspension. The light fleeing that silent giant carries a hidden story, stretched thin by gravity itself. This is the gravitational redshift verification, a subtle but profound transformation of light predicted by Einstein's theory of general relativity. Imagine a photon, a particle of light, struggling to climb out of the immense gravitational well of a 17 billion solar mass black hole. It expends an enormous amount of its energy just to escape, like a rock thrown upward against a planet's gravity, slowing as it rises. But light can never slow down, its speed is constant. Instead, it loses energy in a different way, by shifting to a longer, redder wavelength. The effect is extreme. Light emitted right at the black hole's event horizon would be redshifted to essentially nothing, stretched into undetectable radio waves or beyond. For light coming from stars orbiting just outside that point of no return, the shift would still be dramatic, moving their familiar colors deep into the infrared. Detecting this specific redshift is more than just another measurement. It is a direct test of the fabric of reality under the most extreme conditions imaginable. We have confirmed general relativity in our solar system and with merging black holes, but never this close to such an impossibly massive, quiet singularity. Succeeding here would be like proving the laws of physics inside the heart of a star, using only the faint glow from its surface. The challenge is monumental. First, you must isolate the light from stars that are perilously close to the event horizon, filtering out the overwhelming glare from the billions of other stars in the galaxy. This requires the exquisite angular resolution of an instrument like the James Webb Space Telescope, which can see in the precise infrared wavelengths where this redshifted light would arrive. Then, you must measure the star's spectrum with phenomenal precision, identifying familiar patterns of atomic lines and seeing how far they have been shifted from their normal positions. But there is a cosmic complication. The universe itself is expanding, which also stretches light, causing a cosmological redshift. For a galaxy as distant as NGC 1277, this cosmological effect is huge, and it must be perfectly disentangled from the much smaller gravitational shift you are trying to find. It is like trying to hear a single, soft note played on a piano while standing next to a roaring waterfall, and then determining if that note is slightly flat because of the piano's tuning or because of the humidity in the air. Success would be a triumph of precision cosmology. It would allow us to map the warping of space-time right at the edge of the abyss, confirming that Einstein's equations hold true even in the presence of a gravitational monster that defies all other rules of galaxy formation. A failure, however, would be even more electrifying. If the measured redshift does not match the predictions of general relativity, it could point to new physics, perhaps a sign that our understanding of gravity itself breaks down in such an extreme environment, or that something even stranger is happening around this unique black hole. This faint, stretched starlight is therefore a message in a bottle, sent from the most distorted region of space we can observe, carrying within it a simple question: do the rules still apply where the universe seems to have forgotten its own? A silent, starved giant can still occasionally lash out. Deep within the archives of astronomical surveys, there might be a single, forgotten flash, a brief, brilliant spike of light recorded years or even decades ago, perfectly aligned with the position of NGC 1277. This is the candidate tidal disruption event, the ghost of a stellar murder. It occurs when an unlucky star, perhaps one from that misaligned nuclear disk, or a solitary wanderer, strays too close to the supermassive black hole's event horizon. The black hole's gravity is so intense that the side of the star facing it is pulled much more strongly than the far side. This difference, the tidal force, stretches the star horizontally while compressing it vertically, pulling it apart into a long, thin strand of superheated gas in a process called spaghettification. The stellar debris does not vanish instantly. About half of it is flung away in the darkness, while the rest forms a temporary, swirling accretion disk around the black hole, glowing fiercely as it is consumed. This produces a distinct and terrifying signature, a sudden, rapid brightening across the entire electromagnetic spectrum, from X-rays to visible light to radio waves. The flare rises to a peak over weeks or months, and then slowly fades over the following year as the last of the stellar material falls in, or is blown away. Finding even one such flare in old data would transform our understanding of the black hole's present state. It would prove that the monster is not completely dormant. It tells us that, within the last few decades or centuries, there was still enough stray material, a single star, within its grasp to trigger a cataclysmic feeding frenzy. This changes the timeline from billions of years of silence to a mere blink of an eye in cosmic terms. The properties of that flare would be a detailed autopsy of the event. The peak brightness tells us how much material was devoured. The rate at which the light faded reveals the black hole's mass with independent precision. A cross-check on that impossible 17 billion solar mass figure. The color of the flare, its spectrum, would even tell us what kind of star was destroyed. Was it a hydrogen-rich sun like our own, or an aged, helium-rich core? Each piece of data is a clue to the environment right at the precipice. A single archival flash would be a message in a bottle from the edge of oblivion, confirming that even in the deepest quiet of a fossil galaxy, the most fundamental and violent laws of gravity are still patiently at work. Hidden within the rainbow of starlight from NGC 1277 is a single, anomalous scratch of color. When astronomers spread the galaxy's light into a full spectrum, they find a faint but persistent line at a wavelength that does not correspond to any known atom, molecule, or chemical process. This unidentified spectral line is a ghost in the data, a whisper that science cannot yet translate. It sits there, a tiny spike or dip in the graph, defying every entry in the massive libraries of atomic and molecular transitions compiled over a century of laboratory physics. The hunt to explain it is a masterclass in cosmic deduction, where every possibility leads to a new frontier. The first and most cautious explanation is the mundane. It could be an instrumental artifact, a faint glitch induced by the telescope's own electronics or by the Earth's atmosphere, perfectly mimicking a real signal. Ruling this out requires painstaking repetition, observing the galaxy with different instruments, at different times, and from different observatories. If the line persists, the real mystery begins. Perhaps it is a signature of exotic chemistry. This could be a rare molecule that only forms under the unique, pristine conditions of this fossil galaxy, a compound of elements in a configuration we have never replicated in a lab on Earth. Or it could point to a forbidden transition, a quantum leap within an atom or molecule that is so unlikely under normal conditions that we never see it, but which becomes possible in the incredibly thin, quiet interstellar medium of this ancient place, where atoms can go undisturbed for millions of years. The most thrilling possibility, however, is that this line is a window to unknown physics. It could be the signature of a theorized but never seen form of dark matter particle, something that decays or annihilates and leaves a specific photon as a calling card in the visible spectrum. Or it might be evidence of a subtle shift in the fundamental constants of nature, like the fine structure constant, over cosmic time or in extreme gravitational fields, which would change the precise wavelengths at which atoms absorb and emit light. Each observation sharpens the focus. Astronomers will study the line's exact shape. Is it sharp or broad? A sharp line points to a cold, low-density gas. A broad line suggests hot, turbulent motions, perhaps gas swirling near the black hole. They will check if the line's strength changes in different parts of the galaxy. Is it stronger in the core, or does it permeate the entire stellar population? This spatial map is a clue to its origin. The persistence of this uninvited mark on the data is a humbling reminder. It tells us that for all our cataloging of the cosmos, there are still ingredients in the universe's recipe that we have not named, and processes we have not yet dreamed of. This single, stubborn line is not a flaw in our understanding. It is an edge, a place where our maps of reality end and the true unknown begins. Even the galaxy's grand motion through space holds a subtle, unsettling tremor. Precise measurements from observatories like the Hubble and Gaia have revealed that NGC 1277 might not be moving through the Perseus cluster in quite the way we predict. This proper motion anomaly is a tiny, almost imperceptible wiggle in its path, a deviation from the smooth, expected flow of a galaxy within its cluster's gravitational embrace. To grasp the scale, imagine tracking a single ship sailing across a vast, calm ocean. You know the prevailing currents, you can predict its course, but if you observe with perfect instruments, you might see the ship shudder slightly, its prow turning a fraction of a degree off course, as if tugged by a hidden underwater chain. That shudder is the anomaly. For this fossil galaxy, it means its measured velocity and direction differ from the values calculated by mapping the visible mass of the entire Perseus cluster. Something is off. The first and most tantalizing explanation points to the invisible. The anomaly could be the gravitational fingerprint of unseen mass concentrations within the cluster itself, vast clumps of dark matter, or perhaps entire galaxies shrouded in dust, whose gravity is pulling on NGC 1277 in a way our current maps do not account for. It is a clue written in motion, suggesting that the cosmic neighborhood is even more lumpy and uneven than we thought, with hidden giants subtly steering their visible neighbors. The second possibility rewrites the galaxy's personal history. This unexpected motion could be a relic of its ancient trajectory. Perhaps NGC 1277 did not form in the heart of the Perseus cluster, but was captured by it long ago, falling in on a wild, hyperbolic orbit that is only now settling down. That violent infoul, a plunge through the hot cluster gas, could have been the very event that stripped it of its dark matter and star-forming gas, leaving behind the bare, red relic we see today. The anomaly in its present motion would then be the final echo of that catastrophic entry, the last traces of momentum from a dramatic journey that shaped its entire existence. Each interpretation transforms this slight wobble from a measurement error into a profound clue. It asks whether the forces shaping this fossil are external, coming from a hidden architecture of the cosmos, or internal, the lasting signature of a traumatic birth into the cluster that has been its home for billions of years. The galaxy's path is not just a line through space. It is the first sentence of its autobiography, and we have just found a word we do not yet understand. The faint tremor in the galaxy's motion could be a whisper of a far more energetic process. Somewhere within this silent relic, particles are being hurled into the void at nearly the speed of light. NGC 1277 might be a cosmic ray factory, a hidden accelerator of unimaginable power. Cosmic rays are not rays of light. They are atomic nuclei protons and heavier elements stripped of their electrons and boosted to energies millions of times greater than anything our most powerful particle colliders can produce. They streak across the universe, and when one finally strikes our atmosphere, it creates a brief secondary shower of particles we can detect. But for over a century, their ultimate origins have been one of astronomy's greatest puzzles. Where do these microscopic bullets get their incredible speed? This fossil galaxy, for all its quiet, holds two terrifying engines capable of such acceleration. The first is the simmering interstellar medium itself. Remember that supersonic wind of million-degree plasma, the collective breath of ancient red giants. That hot gas is not still. It is turbulent, filled with shock waves from long-dead supernova and the collisions of stellar winds. These vast, invisible pressure fronts can act like natural particle accelerators. A stray proton, caught in the chaotic flow, can bounce back and forth across a shock wave, gaining a little more energy with each crossing, until it is finally ejected as a high-energy cosmic ray. The second, and far more potent, engine is the silent black hole's violent past. If that monster was ever an active quasar, its relativistic jets would have been perfect cosmic cannons. The intense magnetic fields and twisting geometries within those jets are ideal for scooping up particles and flinging them across the universe. Even though the jets are now silent, the particles they accelerated billions of years ago would still be traveling, their paths bent by intergalactic magnetic fields, making it impossible to trace them back. But there is a way to find the factory. We need a messenger that travels in a perfectly straight line, unaffected by magnetic fields. That messenger is the neutrino, a ghostly, nearly massless particle that barely interacts with anything. Neutrinos are produced alongside cosmic rays when those accelerated protons collide with other matter or light, creating a cascade of particles that decay into these elusive ghosts. If a neutrino telescope like Ice Cube at the South Pole detects a high-energy neutrino, and astronomers can trace its path back to a specific point in the sky, and that point is NGC 1277, it would be a smoking gun. It would mean that right now, in this ancient galaxy, protons are being smashed together with incredible force. Similarly, a specific signature in gamma rays, a diffuse glow from the galaxy's halo, could also point to this ongoing cosmic ray production. Finding either signal would transform our view of this fossil. It would no longer be a still life, but a dormant volcano, its internal engines still capable of forging the most energetic particles in the universe. A reminder that even in cosmic retirement, the capacity for violence remains. The silent heart of this fossil galaxy may be a dance of two shadows, not one. Among the most provocative theories to explain its impossible mass is that the core of NGC 1277 is not a single monolithic black hole, but a binary system. This would be a pair of supermassive black holes, each weighing billions of suns, locked in a tight, whirling orbit around each other, a final, unfinished step in an ancient galactic merger. Imagine two titanic anchors, each capable of devouring solar systems, spinning around a common center of gravity in a cosmic waltz that has lasted for billions of years. This binary hypothesis solves several puzzles at once. It could explain the staggering total mass if two large black holes from two progenitor galaxies spiraled together and then stalled, never quite merging. It might also account for a potential off-center wobble, as the binary's center of mass shifts with their orbital motion. But how could we possibly detect such a hidden duet? Astronomers would hunt for two key signatures, each a whisper of this immense, hidden choreography. The first is a periodic variation in the light from the galaxy's core. As the two black holes whirl around each other, they would drag with them any nearby stars, gas, or dust that survived their gravitational fury. This material, heated and compressed, would glow brightly. But its brightness would not be steady. As the binary orbits, the geometry of this accretion flow would change rhythmically, perhaps blocking our view of one hot spot or enhancing another, causing the core's total light output to pulse with a regular beat. That beat, that predictable flicker over months or years, would be a clock ticking to the rhythm of the binary's orbit. Finding such a periodicity requires patient, long-term monitoring, watching for a signal that repeats with metronomic precision amid the random noise of stellar processes. The second signature is even more fundamental, a tremor in the fabric of space itself. A supermassive black hole binary would be a relentless source of gravitational waves. Unlike the stochastic hum of the background, this would be a continuous, monochromatic signal, a pure tone in the gravitational wave spectrum. As the two giants circle each other, they constantly ripple space-time, sending out waves with a frequency directly tied to their orbital period. Detecting this specific tone, however, is a challenge of scale. The waves from such a massive, widely separated binary would have very long wavelengths and low frequencies, far below what ground-based observatories like LIGO can hear. This is the domain of pulsar timing arrays, which listen for the nanohertz frequencies that would take years to complete a single cycle. The hunt would involve searching for a specific, persistent wiggle in the arrival times of pulses from a network of millisecond pulsars, a pattern that points unmistakably to this one distant, dancing pair. Confirming a binary here would be a landmark discovery. It would mean the galaxy's most defining feature is not a settled relic, but a dynamic, unfinished system, a fossil caught in the very act of a transformation that began when the universe was young. It would also present a profound mystery. Why did the dance stop? What cosmic friction or lack of gas prevented these two monsters from taking the final plunge and becoming one? The answer could lie in the very nature of this dark matter-free, gas-poor environment, a place so empty that even black holes cannot find the traction to finish their union. The faint, primordial gas would be a whisper from the very beginning. If astronomers were to discover a small, cold cloud of pure hydrogen and helium drifting within NGC 1277, it would be like finding a single, undisturbed snowflake from the first winter. This cloud would contain virtually no heavy elements, no carbon, no oxygen, no iron, none of the atomic ash forged in stellar furnaces and scattered by supernova explosions. Its composition would be pristine, identical to the raw material that filled the cosmos just minutes after the Big Bang, before a single star had ever ignited. In a galaxy over 10 billion years old, such a relic should not exist. Every process of galactic evolution works to pollute and heat this primordial gas. The furious starburst that built this galaxy, the stellar winds from its aging giants, even the faint simmering of its hot interstellar medium, all should have either consumed this gas, enriched it with metals, or heated it to the point where it could no longer remain a cold, separate cloud. Its survival, therefore, would be a miracle of preservation. It suggests this pocket of gas was somehow shielded, perhaps tucked away in a dynamically quiet corner of the galaxy's halo, far from the turbulent core and the regions of past star formation. It might have been orbiting in a vast, lazy path, never falling in to fuel new stars, never encountering a shock wave or a hot wind that would have altered its perfect, primitive state. Discovering it would require the most sensitive radio telescopes, tuned to the specific frequency at which cold, neutral hydrogen gas emits its faint signature. The signal would be a whisper within a whisper, a narrow spike in the data revealing not just the presence of gas, but its untouched chemistry. This cloud would be more than an object. It would be a time machine. By measuring the exact ratios of hydrogen and helium isotopes within it, scientists could perform a direct test of the nuclear processes that occurred in the universe's first 3 minutes. They could check the predictions of Big Bang nucleosynthesis with a sample that has been kept in deep freeze for over 13 billion years. Furthermore, its very existence would force a rethinking of how galaxies use their fuel. It proves that NGC 1277 did not completely process all of its original gas. Some of the birth material remains, frozen in time, offering a pure baseline against which to measure every other element in the galaxy. Every star, every planetary nebula, every wisp of dust we see is enriched relative to this cloud. It is the blank canvas upon which the galaxy's entire chemical history was painted, a silent, cold witness to everything that came after, holding within its simple atoms the uncontested story of the universe's first, purest breath. But the galaxy's gravitational secrets are not confined to its single, central giant. Within the dense stellar swarm at the very heart of NGC 1277, a different kind of darkness may be gathering. Over the 10 billion year lifetime of this fossil, countless stars have lived out their cycles and died. The most massive among them ended their lives not with a gentle sigh, but in the violent collapse of a supernova, leaving behind a dense, dark remnant, a neutron star or a stellar mass black hole. In a galaxy as old and dynamically settled as this one, a fascinating process has had ample time to unfold. Through countless subtle gravitational interactions, a sort of cosmic sedimentation occurs. These dark remnants, being the heaviest objects, gradually lose kinetic energy and sink toward the galaxy's center of mass, just like heavy pebbles slowly settling to the bottom of a jar of shaken sand. The result could be a startling concentration, a dense, dark cusp of thousands, perhaps even millions, of stellar mass black holes and neutron stars orbiting invisibly in the inner light years around the supermassive black hole. This invisible swarm would wield immense gravitational influence, while a single stellar black hole, weighing perhaps 10 times our Sun, is nothing compared to the central behemoth. The collective pull of a million such objects creates a powerful, extended gravitational field. This dark cusp would subtly but measurably alter the orbits of the visible stars that dance through the same region. Astronomers mapping the velocities of these stars would find they move slightly faster than expected, if only the supermassive black hole's gravity were at work. The stars would be whipping around as if space itself were heavier, tugged by an unseen audience of dark spectators. This cusp also sets the stage for a unique kind of cosmic violence. In such a crowded environment, these dark remnants are not just drifting peacefully. They are on chaotic, intersecting paths. Close encounters and direct collisions between stellar black holes would be inevitable over billions of years. When two such black holes finally spiral together and merge, they release a torrent of energy in the form of gravitational waves, ripples in space-time that observatories like LIGO and Virgo are now built to detect. A dense dark cusp in a quiet galaxy like NGC 1277 could be a steady factory for these mergers. Unlike the chaotic environments of young star clusters, the ancient, relaxed core of this fossil provides a clean laboratory. The black holes here have had eons to settle into their grim hierarchy, making the rates and masses of their collisions a direct test of our theories of stellar evolution and dynamics in the early universe. Future space-based gravitational wave observatories, designed to listen for the lower frequency waves from more massive mergers, might one day hear the constant, faint crackle from this distant core, a static of collisions telling the story of a dark population we can never see with light. This potential swarm transforms the galaxy's silent center from a single monster's lair into a bustling, invisible metropolis of the dead, where the ghosts of ancient stars continue to shape the cosmos through their silent, gravitational dance. Centuries after the light of its death first washed over the galaxy, the ghost of a star might still be expanding through the darkness. This is the light echo from a historical supernova, a phenomenon where a single, cataclysmic flash from the distant past continues to reveal itself, not from the source, but from the cosmic mirrors it illuminated along the way. Imagine a supernova exploding in NGC 1277 long ago, perhaps when telescopes were first being pointed at the sky on Earth. The initial, brilliant flash of light would have raced outward in all directions at the speed of light. The photons that traveled directly toward us arrived centuries ago, recorded perhaps as a temporary new star in some ancient astronomer's catalog, now long forgotten. But other photons from that same blast took a different path. They raced out at an angle, striking vast, silent clouds of interstellar dust, floating light years away from the explosion. This dust absorbed the brilliant flash and then, over a period of years, re-emitted it, scattering the light in new directions. Some of that re-scattered light is only now, centuries later, finally reaching our telescopes. What we would see is not a point of light where the star died, but a faint, ethereal ring or shell of light, slowly growing larger and fainter as it expands outward from the original site at the speed of light. It would look like a cosmic ripple in a pond, a perfect circle of glowing dust, illuminated from within by a memory. Finding such an echo in this fossil galaxy would be a chance to conduct an autopsy on a star that died before our modern science existed. By analyzing the echo's light with today's powerful spectrographs, we could determine the exact type of supernova it was. Was it the thermonuclear detonation of a white dwarf, or the core collapse of a massive, short-lived star? The spectrum would tell us the chemical composition of the ejected material, revealing what elements that ancient star forged in its final moments and blasted into the galactic void. But the echo is more than a time capsule of the explosion. It is also a probe of the galaxy's hidden anatomy. As the echo expands, it lights up different filaments and sheets of dust in 3 dimensions. By carefully mapping the shape, brightness, and structure of the glowing ring over years, astronomers could reconstruct the complex geography of the interstellar medium in this ancient galaxy. They could determine how dense the dust clouds are, how they are distributed, and whether they take the form of smooth sheets or ragged, turbulent structures. Each subtle dimple or brightening in the ring's surface is a contour line on a map of unseen terrain. This turns a single historical event into a tool for modern exploration, using the delayed flash from a stellar death to illuminate the silent, dusty corridors of a fossil galaxy we could never see otherwise. It is forensic astronomy of the highest order, where the crime scene is centuries cold, but the evidence is still drifting into view, one expanding ring of ghost light at a time. Even the galaxy's most reliable mileposts can lie. Among the ancient stars of NGC 1277, a single, pulsing beacon breaks the most trusted rule in cosmology. This is an anomalous Cepheid variable, a star whose rhythmic heartbeat tells a story that contradicts everything we know about measuring the universe. Cepheid variables are the foundation of the cosmic distance ladder. Their importance cannot be overstated. These are giant stars that pulsate with a regular, predictable rhythm, growing brighter and dimmer over periods of days to months. In the early 1900s, astronomer Henrietta Swan Leavitt discovered the crucial key, the period luminosity relation. She found that the longer a Cepheid's pulsation period, the intrinsically brighter it is. This is a cosmic gift. By simply measuring how long it takes the star to pulse, you know its true, absolute brightness. Then, by comparing that to how faint it appears from Earth, you can calculate its distance with remarkable precision. Cepheids were the first rung on the ladder that allowed Edwin Hubble to measure the distance to other galaxies and discover the expansion of the universe. They are the gold standard, the celestial yardsticks we trust to map the cosmos. But here, in this fossil galaxy, one of these yardsticks is broken. Astronomers would identify this star by its characteristic smooth light curve, its brightness rising and falling like a perfect rhythmic breath. They would measure its period, the time between peaks in its pulsation. Then, they would look at its apparent brightness and use the standard period luminosity relation to calculate how far away it should be. And the answer would be wrong. The star would be either too bright or too dim for its measured period. It is a fundamental mismatch, as if a 1-foot ruler suddenly measured only 10 inches. This single anomaly throws a wrench into the delicate machinery of cosmic measurement. If cepheids here are unreliable, how can we trust the distance to NGC 1277 itself? And if we cannot trust that, how does that affect our understanding of its other impossible properties, like the size of its black hole or the absence of its dark matter? The implications spiral outward. The cause of the anomaly points to the galaxy's strange history. A cepheid's pulsation is an exquisitely sensitive balance between the inward pull of gravity and the outward push of radiation pressure in its outer layers. That balance depends on the star's mass, age, and chemical composition. In the pristine, metal-poor environment of this ancient galaxy, stars formed from gas that lacked heavy elements. This changes the opacity of their stellar atmospheres, how easily light pushes against the material. A star with lower metallicity might pulsate differently, following a slightly altered period luminosity relation. This cepheid could be a pure example of that, a standard candle forged under non-standard conditions, calibrating itself to a different tune. Another possibility is even more intriguing. This might not be a classical cepheid at all, but a different evolutionary beast, an anomalous cepheid subtype. These stars are thought to be the result of stellar mergers or mass transfer in binary systems, creating a bloated, pulsating star with a mass and structure that doesn't fit the classic mold. In the dense, ancient environment of NGC 1277's core, such stellar collisions or interactions could have been more common long ago. This would make the star not a pristine measuring tool, but a product of later dynamical violence, its pulse telling the story of a past encounter rather than its innate properties. Either way, this single, rhythmic star forces a profound humility. It reminds us that our cosmic rules are derived from our local, modern neighborhood. When we venture into a relic from the universe's youth, we must be prepared for the fundamentals to shift. The very tools we use to explore can become part of the mystery, their familiar ticks and flashes now carrying a coded message from a time when the universe built its stars by a different set of plans. The entire galaxy is a single, sprawling crime scene, and its stars are the witnesses. To understand the strangest object of all, you must step back and see NGC 1277 not as a collection of suns, but as a single, intricate map, a galactic archaeological survey written in starlight. This map is not drawn with ink, but with motion and chemistry. Every star in this fossil galaxy carries two vital pieces of information in its light: its velocity, which tells us where it is going, and its spectrum, which reveals its elemental composition, a chemical fingerprint of its birth. By measuring these properties for hundreds of thousands, even millions of individual stars, astronomers can perform a form of cosmic forensics. They can rewind the clock. Stars that move together in coherent streams, like rivers of light flowing through the galaxy, are often the remnants of a single, devoured satellite galaxy, their shared motion a ghost of their original orbit. Stars with a distinct, metal-poor chemical signature might all have been born in the same primordial gas cloud during the galaxy's initial furious burst. It is like reading the rings of a tree, but on a galactic scale. Each ring, each chemical subgroup, each stellar stream is a chapter in the autobiography of NGC 1277. This detailed map would answer the most fundamental questions. Did this galaxy form in one rapid, monolithic collapse, as its uniform old stars suggest? Or does the map reveal faint, tangled streams, the digested remains of many smaller building blocks that came together long ago? The map could pinpoint the precise moment the galaxy quenched, showing a sharp boundary in chemical space. Stars born before a certain time are rich in alpha elements like magnesium from short-lived supernova, while any hypothetical later stars would show the signature of iron from longer-term processes. In a galaxy that appears so simple and uniform, this archaeological map is the ultimate tool for revealing hidden complexity. It could uncover populations of stars that were kidnapped from other galaxies, or identify a small group of stars that formed from a last, gasping breath of star formation long after the main event. Creating this map is a task of almost unimaginable patience and precision, requiring instruments that can dissect the light of millions of faint, distant suns. But the result would be more than a catalog. It would be the definitive life story of a cosmic fossil, a narrative built not from speculation, but from the direct testimony of every star that has ever shone within its silent borders. Etched into the outermost fringes of this ancient relic, a whisper of structure defies its very shape. In the most sensitive maps of its starlight, astronomers might detect faint, arc-like overdensities, gentle swirls in the distribution of its 10-billion-year-old stars. These are not the bold, star-forming arms of a spiral galaxy today, but their fossilized skeleton, the ghostly imprint of spiral arms that once graced NGC 1277 in its youth. This discovery would be nothing short of revolutionary, for it directly contradicts the galaxy's present classification as a smooth, featureless elliptical. It suggests a dramatic rebirth, a fundamental transformation from one cosmic identity to another. We must reimagine this fossil's past. It may not have been born as this dense red sphere. Instead, it could have begun its life as a magnificent spiral, a grand design disk of gas and young stars, spinning gracefully in the early universe. Then something catastrophic happened, and it happened fast. The leading suspect is its environment. Plunging into the dense, hot core of the Perseus cluster for the first time, the galaxy would have experienced a violent process known as ram pressure stripping. Imagine this pristine spiral sailing at millions of miles per hour through the thin, superheated gas that fills the space between galaxies in a cluster. That intergalactic plasma acts like a torrential cosmic wind. It does not tear the stars apart, but it does something just as effective. It scours away the galaxy's lifeblood, the cold, dense gas and dust that resides in its spiral arms, and fuels new star formation. The process is brutally efficient. The galaxy's own gravitational grip cannot hold onto this gas against the relentless headwind. It is stripped away like topsoil blown from a field in a hurricane. In a relatively short time, cosmically speaking, the spiral arms bereft of their star-forming material would fade. The bright blue clusters of young stars would age out, leaving behind only the older, redder stellar population. The delicate disk, no longer sustained by new dynamics, would likely thicken and puff up through gravitational interactions, morphing into the smooth, elliptical shape we see today. This transformation, this quenching, had to be extremely early and utterly decisive. The fossil spiral arms we see are only the oldest stars, the ones that were already formed before the great stripping began. There is no younger generation to overwrite their pattern. They are the enduring bones of a structure that died in its infancy, a galactic butterfly that never left its chrysalis, forever frozen in the moment of its transformation. This faint swirl in the starlight is therefore more than a curious shape. It is a death certificate. It records the precise moment this galaxy's future was stolen, its spiral destiny cut short by the violent environment into which it was born, leaving behind only this ghostly signature of what it was always meant to be. The galaxy's faint spiral ghost tells a story of violent loss, and the thief is still present all around it. NGC 1277 is not floating in empty space. It is submerged in an invisible, searing ocean. This is the intracluster medium, the thin but unimaginably hot plasma that fills the vast spaces between galaxies in the Perseus cluster. To call it thin is a cosmic understatement. It is 1,000,000 times less dense than the best vacuum we can create on Earth. But it is also heated to temperatures of tens of millions of degrees, a broth of charged particles that glows faintly in X-rays. This is the true environment of the cluster, a diffuse, superheated atmosphere that exerts a force more powerful than any visible gravity. As NGC 1277 moves through this plasma at speeds exceeding 1,000,000 miles per hour, it experiences a relentless cosmic headwind. This is RAM pressure stripping, and it works with brutal simplicity. Picture a galaxy as a vast collection of stars, like a swarm of bees. Between those stars is the cold, dense gas that is the raw material for making new bees, new stars. Now, imagine that swarm flying at tremendous speed through a gigantic, invisible furnace. The hot plasma does not stop the bees, the stars, but it does violently interact with the gas between them. The cold, dense gas clouds within the galaxy feel an immense drag force, a pressure pushing directly against their direction of motion. It is like holding your hand out the window of a speeding car. The force you feel pushing your hand backward is RAM pressure, but on a galactic scale and against clouds of gas light years across. The galaxy's own gravity tries to hold onto this gas, its lifeblood. But for NGC 1277, moving so quickly through such a dense region of the cluster, the RAM pressure wins. Over hundreds of millions of years, the wind is constant and unyielding. It does not gently blow the gas away, it scours it, peeling it layer by layer from the galaxy's grasp. The cold gas clouds are torn from their orbits, shredded, and heated until they join the hot intracluster medium itself, lost forever. This process is the most likely culprit for the galaxy's profound starvation. It explains the lopsided dust lane, perhaps the last twisted remnant of a gas reservoir being actively stripped. It explains the complete absence of young blue stars. There has been no cold gas left to collapse and form them for 10 billion years. The RAM pressure did not just strip the gas, it permanently quenched the galaxy, cutting off its future in one relentless, eons-long act of cosmic erosion. The galaxy we see today is a skeleton, a stellar framework stripped clean of the fertile material that gives most galaxies their vibrancy and life. It is a fossil not because it died of old age, but because its environment executed a perfect, slow-motion robbery, leaving behind only the bones of its original, glorious form. But the violence of that ancient stripping may have sparked a strange and opposite creation. Clinging to the outskirts of this fossil galaxy, a knot of stars and gas seems to tell its own story of rebellion. This is a tidal dwarf galaxy candidate, a clump of material that was not consumed, but violently expelled. The process is one of cosmic chaos, during a past, close gravitational encounter. Perhaps with another member of the Perseus cluster, immense tidal forces would have stretched both galaxies like taffy. Long streamers of stars, gas, and dust would have been pulled out from their main bodies, arcing into the intergalactic void. Most of this material eventually falls back or disperses. But in the densest, most massive knots within these tidal tails, something miraculous can happen. Gravity can take hold. The clump, now free from the immediate pull of its parent galaxy, can begin to collapse on itself. Within this orphaned pocket of cosmic debris, the gas can cool, condense, and ignite with the fire of new stars. What was once a piece of a galaxy can become a galaxy itself, a newborn system forged not from pristine primordial gas, but from the recycled wreckage of a collision. The irony is profound and beautiful. Here we have NGC 1277, a galaxy frozen in time, a relic whose own star formation ceased over 10 billion years ago. Yet, through the gravitational turmoil of its more recent past, it may have inadvertently given birth to something new. This tidal dwarf candidate would be a living contradiction, a youthful star-forming entity clinging to the halo of an ancient, red and dead fossil. It is a galactic phoenix, but one born from ashes that are themselves billions of years old. Confirming its nature is a delicate task. Astronomers must prove it is gravitationally bound, a true island universe and not just a transient cloud. They measure the velocities of its stars and gas, checking if they move together as a cohesive unit, held by their own collective gravity rather than just flowing along a tidal stream. They also analyze its starlight, looking for the blue signature of young, hot stars, a clear sign of recent birth that would stand in stark contrast to the uniform red glow of its ancient parent. If confirmed, this object forces us to expand our definition of what a galaxy can be. It shows that galactic birth is not a process confined to the early universe. New galaxies can be assembled at any time, from the debris of old ones, in the unlikeliest of nurseries, the violent, empty spaces left behind after a close call. This potential dwarf, then, is more than a strange object. It is a testament to the universe's endless capacity for reinvention, proving that even from the deepest stillness of a cosmic fossil, new life can be violently, unexpectedly spun into being. The galaxy we call NGC 1277 might be more than a cosmic oddity. It could be a fossil of the universe's first whisper. To understand this, we must look beyond stars and black holes, back to a moment before time itself had meaning. In the first fraction of a second after the Big Bang, the universe was not smooth. It was a seething quantum foam, a realm where empty space itself was not empty, but alive with fleeting, random fluctuations in energy. Particles and antiparticles blinked in and out of existence, creating microscopic ripples in the density of the cosmos. These were not flaws, they were the seeds of everything. As the universe expanded and cooled, gravity began to work on these tiny imperfections. Places that were ever so slightly denser than average had a tiny bit more gravitational pull. They attracted more matter, growing denser still, in a feedback loop that spanned billions of years. The grand tapestry of galaxies we see today, the vast cosmic web of clusters and voids, is the magnified, grown-up version of those initial quantum ripples. Most galaxies formed from average peaks in that primordial density field. But NGC 1277 is not average. Its bizarre collection of properties, the monstrous black hole, the missing dark matter, the ancient pristine stars, might all be signatures of something far more profound. This galaxy could be the macroscopic fossil of an extreme quantum fluctuation. It may have grown from a single, spectacularly high peak in the universe's initial density field, a statistical outlier so pronounced that when it collapsed, it did so in a way that broke all the standard rules. Think of the early universe as a vast, rolling landscape of hills and valleys created by those quantum ripples. Most galaxies formed from modest hills, but NGC 1277 might have formed from a single towering mountain, a peak so sharp and isolated that its gravitational collapse happened with incredible speed and violence. This could explain the impossible black hole. In such a dense, concentrated peak, gas could have funneled directly to the center with staggering efficiency, building a gargantuan seed black hole in one swift, catastrophic event, bypassing the slower, merger-driven growth of normal galaxies. It could also explain the strange absence of dark matter. In this model, the dark matter and normal matter might have been separated during that violent, monolithic collapse, with the normal matter sinking to the center to form the stars and the black hole, while the dark matter was somehow scattered or expelled. And it perfectly explains the fossilized stars. A collapse this rapid would have used up all the available gas in one furious burst of star formation, leaving nothing behind for future generations, creating a galaxy that was essentially born old, a finished product when the universe was still in its adolescence. This perspective transforms NGC 1277 from a mere curiosity into a direct link to the universe's quantum origin. It is no longer just a strange galaxy. It is a time capsule containing a magnified imprint of the universe's first moment, a cosmic photograph of a random quantum event, blown up to a scale of billions of stars. We are not just looking at a relic of stellar evolution. We might be staring at the preserved echo of the Big Bang's first chaotic breath, frozen in the form of a silent red giant. The profound silence of this fossil galaxy extends beyond the absence of starlight. We have listened for a different kind of whisper, one born of intelligence, and heard only the deeper quiet of the cosmos. Across decades, radio telescopes have scanned the heavens, patiently sifting through the cosmic static for any pattern, any signal that bears the unmistakable mark of design. This search for extraterrestrial intelligence has swept over countless star systems, including the ancient suns of NGC 1277. The result from this particular relic is a definitive nothing, a complete lack of any artificial radio transmissions or other technological signatures. This null result is not a failure, it is a profound piece of data etched in silence. In a galaxy whose stars are over 10 billion years old, life had an immense head start. If intelligence were a common, inevitable outcome of cosmic evolution, this would be the perfect place to find its evidence. Think of it as a cosmic experiment that has been running for twice as long as our own solar system has existed. The planets there, if any exist, have had billions of years more than Earth to develop civilizations, to master their environment, to build, to communicate, and perhaps to reach for the stars. The fact that we detect no engineered signal from that vast expanse of time suggests a sobering possibility. It implies that the emergence of a technologically advanced species may be an exceptionally rare filter in the great chain of cosmic evolution, a step so difficult that even 10 billion years of trial and error on countless worlds might not guarantee its success. This silence could mean many things. Perhaps life itself is rare in such metal-poor, ancient environments. Maybe biological intelligence arises but rarely survives its own technological adolescence, succumbing to self-destruction or stagnation long before it can broadcast its presence across the gulfs between galaxies. Or it could be that advanced civilizations evolve in ways we cannot yet imagine, using technologies that are completely undetectable to our primitive radio ears, leaving no signature we would recognize. This single, silent data point from a fossil galaxy adds weight to a haunting perspective. It suggests that even in a universe teeming with ancient stars, the spark of conscious, technological awareness may flicker only briefly or not at all, leaving the grand cosmic story to be told by physics and chemistry alone, witnessed by no one. Deep within the galaxy's silent heart, gravity does more than just bend light. It warps time itself. The region immediately surrounding the supermassive black hole is not just a place of immense pull, but a gravitational time dilation zone, a natural laboratory where the universe's most fundamental rules are stretched to their breaking point. According to Einstein's theory of general relativity, time is not a universal constant. It flows at different rates depending on the strength of the gravitational field you are in. The stronger the gravity, the slower time passes. Here, next to a mass of 17 billion suns, this effect is not a tiny theoretical quirk. It is an overwhelming, dominant force shaping reality. If we could place a hypothetical, indestructible clock in a stable orbit close to the black hole's event horizon, and compare its tick to an identical clock far out in the galaxy's peaceful halo, we would witness a staggering divergence. For every single second that passed on the clock near the black hole, years, decades, or even centuries might flash by on the distant clock. The difference would be that extreme. This means an observer brave enough to orbit that close would experience time in slow motion. Their heartbeat, their thoughts, their very perception of reality would grind to a crawl. But when they looked outward, the universe would appear to be a frenetic, high-speed blur. They would watch as stars in the distant halo completed entire orbits in what felt like moments. They would see the gentle, billion-year dance of galaxies in the cluster outside appear as a frantic, swirling whirlpool. The entire cosmos beyond their bubble of extreme gravity would seem to be rushing headlong into the future, aging and evolving at a breathtaking, terrifying speed. This is not science fiction. It is a direct prediction of our most well-tested theory of gravity. We cannot send a probe there, but we can look for the signatures of this time warp in the light from stars that do orbit close to the monster. Their light, struggling to climb out of that deep gravitational well, is not only redshifted, but the very frequency of its atomic vibrations, its own internal clock, is slowed from our perspective. Finding and measuring this effect with precision is one of the ultimate tests of general relativity. This zone transforms the black hole from a simple mass into a cosmic time machine. It creates a pocket of the universe where the present is stretched thin, and the future of everything else is on fast forward, a perfect, natural demonstration that time itself is a fluid, malleable dimension, bent by the weight of a sleeping giant. This silence is not empty, but threaded with faint, unraveling rivers of light. Winding through the outer halo of NGC 1277 is a stellar stream so delicate it seems drawn with a single hair. This is the ghost of a globular cluster in its final act of dissolution, a string of pearls pulled apart by the relentless, invisible tides of the larger galaxy. Globular clusters are normally tight, spherical knots of ancient stars, bound together by their mutual gravity for billions of years. But this one ventured too close to the dense, central mass of the fossil galaxy. The difference in gravitational pull between the side of the cluster nearest the galaxy and the side farthest away created a stretching force, a tidal pull, that began to overwhelm the cluster's own self-gravity. It is a slow, cosmic unraveling that has been proceeding for eons. The cluster did not explode. It is being spaghettified, its stars gently teased out from the main body to form a long, thin arc that now traces the corpse's final orbit around its destroyer. This stellar stream is more than a relic of destruction. It is a precision tool. Every star in that stream is a test particle, a single marker moving under the sole influence of the galaxy's total gravitational field. By meticulously charting the path of this stream, its curvature, its width, the precise positions of its stars, astronomers can perform a remarkable kind of reverse engineering. They can map the shape of the invisible well of gravity that is sculpting the stream's trajectory. Think of it like tracking the flow of water in a river. The water's path reveals the contours of the hidden riverbed beneath it. In the same way, the stream of stars reveals the contours of the galaxy's gravitational landscape. This is crucial for solving the central mystery of NGC 1277's missing dark matter. The stream's path tells us how much total mass is inside its orbit, and where that mass is concentrated. If the galaxy truly lacks a dark matter halo, the stream's orbit will be shaped almost entirely by the pull of the visible stars and that monstrous central black hole. Its path will be a clean, predictable ellipse, but if there is unseen mass dark matter distributed in a hidden halo, the stream's trajectory will be subtly different. It might show a slight warp, a deviation that betrays the presence of an extended, invisible gravitational source. The width of the stream itself is another clock. A thin, needle-like stream suggests the globular cluster was disrupted a very long time ago. The stars have had billions of years to spread out along their similar orbits, creating a smooth, narrow ribbon. A thicker, more clumpy stream points to a more recent disruption, where the stars have not yet had time to fully separate. By measuring this width and modeling the dynamics, scientists can estimate not just where the mass is, but when this act of cosmic consumption began. This turns a single, fading scar into a historical record. It tells us that even this fossil galaxy, for all its isolation, is not completely inert. Its gravity is still at work, slowly processing the ancient companions from its youth, digesting them over timescales that dwarf human history. The stream is a live readout of an ongoing process, a silent testimony to a force that works with infinite patience, writing its signature in the scattered light of a billion dying suns. A ring of stars, tilted at a perfect 90-degree angle, would encircle this fossil galaxy like a celestial hula hoop. This is the concept of a polar ring, a rare and spectacular structure where a vast disk of stars, gas, and dust orbits perpendicular to the main galaxy's plane. For a smooth, ancient elliptical like NGC 1277, such a feature would be the ultimate cosmic contradiction. It would be an imposter's crown, a piece of borrowed finery that tells a story of theft on a galactic scale. True polar ring galaxies are thought to form through a very specific act of cosmic piracy. A smaller, gas-rich galaxy ventures too close to a larger elliptical on a perpendicular orbit. As it is torn apart by tidal forces, its material is not immediately consumed. Instead, it is stretched out into a vast, looping stream that eventually settles into a stable, rotating ring around the larger galaxy's poles, a glittering band of stolen starlight spinning at a right angle to everything else. Finding even a hint of such a structure here would force a radical rewrite of this galaxy's quiet biography. It would be undeniable proof of a major, relatively recent accretion event, a dramatic merger that happened long after its initial star formation had ceased. This would shatter the image of NGC 1277 as a perfectly isolated relic. It would reveal a hidden chapter of violence, a moment where it reached out and cannibalized another system, not to create new stars, but to adorn itself with a trophy of its conquest. The ring's composition would be the key to the crime. If it were made of young, blue stars and rich gas, it would signify the captured remains of a vibrant, star-forming dwarf galaxy, its life cut short and its material repurposed as decoration. If, however, the ring were composed of ancient red stars, a fossil ring, it would point to an even older, more patient theft. It could be the remnant of a galactic merger from the early universe, a ring that has been orbiting in perfect, silent equilibrium for 10 billion years, a permanent scar from a collision that happened when the cosmos was young. This polar ring, real or hypothetical, is more than just another strange object. It is a test of the galaxy's purity. Its absence reinforces the story of profound isolation. Its presence, however faint, would paint a portrait of a dynamic survivor, a galaxy that has been quietly accumulating the wreckage of its neighbors for eons, wearing their remains as a tilted, twisting crown in the dark. The light from those ancient stars is more than a fossil record. It is a universal benchmark. The galaxy's extreme age and pristine state make it a perfect laboratory for a question that strikes at the very foundation of reality. Have the laws of physics themselves remained constant? Could the fundamental numbers that govern the universe, like the strength of electromagnetism or the mass of an electron, have been different 10 billion years ago? NGC 1277 offers a unique chance to find out. This concept hinges on a specific, measurable quantity called the fine structure constant. It is not a single law, but a magic number that appears in the equations of quantum electrodynamics. It determines how strongly light and matter interact, setting the strength of the electromagnetic force that binds atoms together. Its value, approximately 1/137, is woven into the very fabric of our reality, dictating the energy levels within every atom. If this number were even slightly different in the distant past, it would leave a distinct fingerprint in the ancient starlight we see today. Here is how the test works. When astronomers take a high-resolution spectrum of a star, they see a forest of dark absorption lines. Each line corresponds to a specific atom, like iron or magnesium, absorbing light at a precise wavelength as it moves from one quantum energy level to another. The exact spacing between these lines is set by the fine structure constant. If that constant had a different value when the light left NGC 1277 10 billion years ago, the pattern of lines in its spectrum would be subtly shifted compared to the same pattern measured in laboratories on Earth today. It would be like listening to a song played on a piano that was tuned slightly differently a long time ago. The melody is recognizable, but every note is a tiny bit off key. Detecting this shift is an exercise in almost unimaginable precision. The expected change, if any exists, is minuscule, perhaps a shift of just one part in a million over 10 billion years. To measure it, astronomers need the cleanest possible signal. This is where the fossil galaxy's purity becomes essential. In a typical galaxy, the light is a messy mixture from stars of many different ages and chemical compositions, each with their own spectral quirks that can mimic or hide the subtle signal of a changing constant. But in NGC 1277, every star is a contemporary, born from the same primordial gas at the same ancient time. Their collective light provides a single, coherent snapshot of physics at a specific moment in cosmic history. Analyzing this light requires instruments of extraordinary stability and sensitivity, like the spectrographs on the Very Large Telescope or the future Extremely Large Telescope. They must collect photons for hours, even nights, to build a signal strong enough to dissect. The data is then compared, line by delicate line, against ultra-precise laboratory measurements made on Earth. Any consistent, minuscule drift across many different elements would be the smoking gun. The implications of such a discovery would be staggering. It would mean the rules of the game are not fixed. The universe's operating manual has been subtly rewritten over time. This could point to entirely new physics, perhaps extra dimensions that were more influential in the early cosmos, or a dynamic field that has slowly evolved since the Big Bang, gently tweaking the forces of nature as it changed. Conversely, a null result from this fossil galaxy would be equally profound. It would place the tightest constraints yet on the constancy of nature, confirming that the laws we measure here and now are the same laws that have governed the cosmos since its first stars ignited. In this silent red giant, we are not just looking at ancient suns. We are using them as the most stable, most distant calibration tool ever conceived. A 10-billion-year-old ruler against which we can measure the steadfastness of reality itself. NGC 1277's impossible collection of properties culminates in a final, meta-mystery that challenges not just our observations, but our entire framework for understanding the cosmos. This is the 50th strange object, the simulation glitch. It is not a physical thing you can point a telescope at, but a profound philosophical puzzle born from the galaxy's very existence. When a single celestial object defies not one, but multiple foundational pillars of astronomy, the correlation between black holes and galaxy size, the universal presence of dark matter, the very process of galactic aging, it forces a humbling question. Are we looking at a bizarre outlier, a one in a trillion cosmic fluke? Or is this fossil galaxy a glaring sign that our understanding of how the universe builds its largest structures is fundamentally incomplete, perhaps even wrong? The feeling is uncanny, as if we have stumbled upon a line of code that does not compute. In a perfectly simulated reality, the rules would be consistent. Galaxies would follow the elegant models we have built from studying thousands of others. They would have dark matter halos. Their central black holes would be proportional. They would evolve in predictable ways. NGC 1277 breaks every single one of these programmed expectations. It behaves like an entity from a different set of physical laws, or like a glitch where the parameters were set incorrectly at the beginning of time. Its monolithic black hole is a value entered with too many zeros. Its missing dark matter is a variable that was never initialized. Its pristine, ancient stars are a process that terminated far too early, leaving the program frozen on a single frame for 10 billion years. This playful analogy of a cosmic glitch is more than just science fiction. It is a powerful metaphor for scientific revolution. Throughout history, the objects that did not fit the prevailing model have been the keys to deeper truth. The anomalous orbit of Mercury hinted at the curvature of space-time. The unexplained speed of distant galaxies revealed an expanding universe. NGC 1277 stands as a modern anomaly of similar magnitude. It is a celestial rebel that refuses to follow the rules, and in doing so, it points directly to the limits of our current knowledge. The galaxy is not broken, our models are. Its existence is a demand, written in starlight, for a new chapter in astrophysics. Perhaps this fossil is not a glitch, but a feature, a representative of an entirely unknown class of galaxies that formed under rare, extreme conditions in the early universe. Our telescopes have simply not been powerful enough to find many others like it. Or maybe it is a sign that the processes we consider universal, like the slow growth of black holes through mergers, are just one path among many. The universe might allow for shortcuts, for freak events where a galaxy can be born fully formed with a monstrous heart, skip the dark matter scaffolding, and then retire almost immediately. This single, silent giant in the Perseus cluster is therefore a teacher. It is not here to confirm what we already know, but to show us what we have missed. Its greatest gift is the profound unease it creates, the thrilling sense that the cosmic story is far stranger and far more wonderful than we ever imagined. NGC 1277 is not just a collection of stars, it is a cosmic manifesto. Every one of its 50 strange objects is a signature of defiance, a deliberate break from the universal rules we thought we understood. From its grotesquely oversized black hole to its missing dark matter soul, from its fossilized spiral arms to its potential binary heart, this galaxy refuses to fit into any of our carefully labeled boxes. It is a rebel, a galactic heretic that has followed its own mysterious path for over 10 billion years. Studying this place is not like reading a standard chapter in the universe's history book. It is like finding a secret, forbidden appendix, written in a language we are only just beginning to decipher. Each strange object is a sentence in that text, revealing a story of extreme birth, violent environment, and profound isolation. Together, they paint a portrait of a universe far more creative and far more strange than our standard models ever allowed. This fossil is not an error. It is a priceless relic, a preserved specimen from a time when the cosmos was experimenting with how to build its grandest structures. It challenges us to think bigger, to question deeper, and to admit that for all we have learned, the universe still holds profound surprises in its oldest corners. So we turn the question to you. After this journey through 50 mysteries, which strange object captured your imagination the most? Was it the silent, starving black hole, the ghostly spiral arms, or the faint possibility of a changing law of physics? Let us know in the comments below. If you enjoyed this exploration of cosmic rebellion, please give this video a like and subscribe for more journeys to the edges of our understanding. The next time you look up at the night sky, remember that hidden among the familiar points of light are fossils like NGC 1277, silent rebels holding the keys to the universe's deepest and strangest